Hey everyone, welcome back to the channel. Today we are learning about the decision tree, a powerful and intuitive machine learning model. We will explore how these tree-like structures make decisions, and then we'll take it a step further by learning about powerful ensemble methods like random forest. This is a live tutorial we've compiled as an in-depth decision tree guide just for you. By the end of this video, you will have a solid understanding of these techniques and how to apply them to real-world problems. Let's get started. But before we begin, make sure you subscribe to our channel and hit the bell icon for more updates on our new videos. First, we'll understand decision trees, the algorithm and the model, right, using a classification case, right? Then I'll give you some hints on what to look for when you look at regression trees. So this is something that I would recommend everyone to do additional reading on because everything is more or less the same except a few things. So I'll come to that. I'll just mention what could be the differences and allow you to explore the regression part on your own. Anyway, we'll get into that. And finally, we'll look at the demonstration of decision trees. We'll implement it on a fairly standard data set. And that's how I've designed this session. So classification using decision trees. First, let's think about, the motivations. We have logistic regression, for example, all right? Why should I be interested in decision trees? So just think in terms of curves versus corners. If you remember logistic regression, it is essentially a case of optimizing a curve or a boundary, right, that separates classes or that separates the categories of a class. So suppose your target variable is churn. Okay, let's take the example from linear regression or maybe or just churn, right? Churn means what? Churn means a customer leaving your service or leaving your subscription. That is churn. So logistic regression can be used to separate the yes churn, that is people who leave the service, and no churn, right? You can use a curve to separate. So if you see curves versus corners, this one is a simple curve, right? A line in mathematics is also called, a straight curve. So that's a simple curve. You can also have quadratic curves, right? You can have cubic curves and things like that. And the last image here, the last graph here, you can see that it has sharp edges. So it is not a single curve. It is a set of linear conditions. Okay. Now, just see the four graphs, right? Which of these graphs is doing the separation between the red and the blue points the best? If you ask that question, obviously and visually, the answer is the square, right, or the rectangle. The reason for this should be fairly obvious, correct? The reason is that you can't control a curve which is based on a single mathematical formula, right? Whether it's cubic, logistic, whatever, right? You cannot control how it behaves in various places or in the data space. You cannot control that. So for example, this cubic curve on the bottom left, here it looks nice. Okay, here all the red points are on top, all the blue points are below. It looks nice. But the curve actually continues down infinitely like this, right? It continues down infinitely. And new points, right? New red points, for example, if they fall somewhere here, right? New red points, if they fall here, then these will be classified as blue. And the cubic actually is going to have another, minimum somewhere, and then it's going to start coming up, right? Cubic is going to be like this. Same way for quadratic also, it will have a sort of curvature, right? And you can't always guarantee a clean separation. So this is a slightly different idea. Okay, decision trees follow a slightly different idea where the idea is not to fit a formula. So it's not for example, logistic formula, you just take the linear regression expression, you put it in the exponential, correct? So the idea is not to take a formula but to find out a set of linear conditions. We'll go a little deeper into this. Okay, quickly just looking at the data set that we are going to be using. And as you know, for the conceptual part, we will use a smaller data set so that we can track the points, the data points, and understand what's going on. For the demo, we'll use a more standard data set. Okay. So this is again, I think, the same coffee shop churn data set. In the linear regression case, I think we were predicting expenditure amount on coffee, customer expenditure or something like that, if I remember correctly. And in this case, let us predict churn. Okay, so the target variable here is churn, and the data points are all exactly the same. Yes, RT, Darshan, Isha, we all have the same data points as before. We have the gender, job, income, age, and we also have the amount, expenditure. Okay, we also have the expenditure of these people in my coffee shop. Okay, and suppose this is historical data, right? Suppose RT churned. Okay, churn means RT stopped coming to my coffee shop. Okay, Darshan did not churn, which means Darshan is still coming to my coffee shop. Okay, and the task is very clear. The task is, can we build a model to predict whether my new customer, based on the gender, job, income, age, whatever, is going to churn or not after say 6 months, whatever. So of course you can build a logistic for this. I would urge everyone to try logistic models, logistic regression models later. We'll focus on decision trees right now. Okay, so first we'll start off with decision trees using a single feature. Okay, to understand the algorithm fully, we'll start with a single feature. Suppose on the right you can see the data set. Okay, suppose I take amount, that is the expenditure on coffee, as my input. Okay, this is my input, and I want to use the amount variable to predict churn. Okay, so the input feature I'm using is amount, that is the amount of money spent on my coffee, right, by these customers, and I want to use that only single variable. I want to use that to classify or predict who is going to churn and who is not going to churn. So on the left side you have the amount axis, right? I'm using one feature, so I'm having the amount axis. All the 10 data points, you can see I have plotted them on this axis. Okay, so judging by the number on the axis, you can actually match who is who, right? So this person has less than 1500 expenditure. If you quickly look at the data set, it looks like Zishan, right? This person has the maximum expenditure, this blue dot, right? And that seems to be, I think, Trevor, right? Trevor has $2642 dollars spent on coffee. Okay, and the labels have been given to you here, right? So blue color will represent those who churned. So Aarti, Gayatri, Jasmine, Monisha, Trevor, right? These people have churned, right? And the red one is no churn. Okay, so Darshan, Isha, Hemant, Lokesh, and Zishan, they did not churn. So now the question is, the goal is, and you have written it down here, the goal is to come up with a series of conditions, and I should say linear conditions. Okay, series of simple linear conditions that break up the data space. So what you're seeing here right now is my data space, this amount axis with the labels. Both the information is there. Single feature amount, that's there in the axis. Okay, you can call it x-axis if you want, amount axis, and the label. Okay, whether they churned or not, that is also there in the color coding. So this is my data space. Okay, the idea is to break this into pure or homogeneous chunks, and then later I will use the condition that I used to break as my predictor. Very simple. We will do an example right here in this slide. Suppose, and I think everybody would like to break it, exactly in that point, because it's so nice. This side we have 4 blue points, this side I have 5 red points and just 1 blue point. So very nice, almost nice split, correct? So this is around, it looks like $2030, $2050. So then I can say anybody less than $2050 looks like they will not churn. That's what my data is telling me. And anybody spending more than $2050, they will churn. Essentially, this is what decision tree is all about. Okay, so if till now the audience has understood what I said, you have more or less understood decision trees. The algorithm is more or less understood. Now we need to go and see the details. How do we do it step by step? What kind of metrics do we use? What are the loss function to use? So on and so forth. But the idea is just this. It is so simplistic, which is why it came as a good competitor for other slightly more mathematical models like logistic regression and things like that. Okay. Anyway, so let us see how this is built step by step. I'll turn my video off for a while. Okay, for this part. This, as we saw, is the data space. Okay, so this is where I have all my original data points. Remember that I am using the amount spent by the customer to classify or predict whether they are going to churn or not. Okay, so I have all the different customers here on the amount axis based on how much they spent on the coffee. So this is the original data space. In a decision tree, this original data space is called the root node. Okay, you can call it the root node, the zeroth node, master node, whatever. The technical term that we use is root node. This is where the tree starts. And also, I think from the slides, it's obvious that the tree is going to be built downwards. It's like a inverted tree. It's not a normal tree, but this is how we represent. Okay, and this is called the root node because everything comes from here. So we start off with the root node. Okay, the root node has all my data points, and if you count, there are 10 data points. Okay, so I have 10 of my data points here. Now the next step is to choose a decision split. Right, the next step is you choose a decision split. Now how to choose the good decision split is something we will see a little later. After we understand the full algorithm, then we will look at how do you find out where to split. For now, suppose that I start my split at this value, whatever this value is. Looks like around 2000, 30, 40, 50, something like that. Okay, suppose I split here. So you can see by splitting here, what is happening is on the left side I have mostly red points, and on the right side I have mostly blue points. Okay, so what does the condition look like? The left condition is basically amount less than equal to 2032. Okay, question is this condition true? So all the data points whose expenditure is less than 2032, which I believe is the value on the amount axis here, all the data points who spent less than $2032 will go to the left side, and if the condition is false, that means everyone who spent more than 2032 will go to the right side. It's very simple, right? And you will get the corresponding groupings in the next level. Okay, so you start out at level 0. Now the size of the tree is 1. Okay, now the height of the tree, you can say, is 1. So you start at 0, and now this is step 1. So you just populate the points, that's all, right? These points, these 5 red points and this 1 blue point, they are all less than 2032, so you put them here. And these points who are all more than 2032, you put them here. Very simple, right? Now what you will immediately notice is that there is no impurity in this group. In other words, I can make 100% correct statement about this group, right? Is there a need to make more splits in the right side group? The answer is no. Why should we split it anymore? Here everything is blue, and I believe blue is churn. Yeah, blue I think is churn. So what my data is telling me is that people who spend more than $2032 as per my training data, 100% will churn. This is what it is telling me. Now if you look at this side, there is some impurity, right? It's red and blue, so we can still make some decision splitting on the left group. So basically, when we stop splitting, the act of not splitting anymore creates something called a leaf node. Okay, and these leaf nodes are essentially the decision makers. We will see that soon. And if you still feel that there is some decision to be made, right, then we will call it a decision node. and I've just done some color coding here, purple for leaf node and orange for decision node. This is obviously not there's no rule. You can color code or whatever it is however you want. You will find decision trees online represented in many different ways. Okay, so not to worry as long as you understand the concept. So here I still have a decision. So let's go ahead and do that. Suppose on the top, now you see on the top, suppose now I choose another decision split. I don't know, this looks like 1700 or something like that. Okay, where is this decision split being applied? It is only being applied to the left subregion. Okay, so it is only being applied on this group of points, these 5 red points and blue point. This side there is no more decision splitting going on. Okay, so on the left subregion now I can have another decision split, and it looks like 1700 or something. We will see what that value is. Okay, it is 1770. So again notice that the splitting variable is still amount. Okay, I started off by saying that I want to classify or predict whether my customer will leave, not come to my coffee shop or not, based on a single feature. So the same feature can be used to split subregions into further subregions. So now if you choose 1770 as your split for the left side subregion in level 1 of the tree, now you will get new subregions. Correct? You will get new nodes, new groupings. And in this new grouping, you can see everybody to the left that is less than 1770 are all red. So they are all going here. And everyone greater than 1770, they have been put here. Okay, blue, red, red. Now I think little bit in your mind you must be thinking how the decision splits are made. As I said, we will come to that a little later. Okay, but supposing that this is a good decision split, which I think it is good. You can split at 1770, which is here. You can also split a little bit more, 1790, whatever. Okay, but which one is better, we will see. So anyway, so once you do that, immediately you can see here is a leaf node. Okay, so now you have another leaf node which is fully pure, and this is still impure. Okay, so the concept is very simple. Pure nodes will not require further splits, whereas impure nodes may be split further. Then what's going to happen? The decision tree is just going to continue building more branches in this way. It is just going to continue with more branches and more levels until it reaches full purity for all leaf nodes. You can keep splitting till it reaches purity for all leaf nodes. And once the tree is complete, then we can assign the labels. Okay, once the tree is complete, then what you do, you essentially see all the leaf nodes and then you say, okay, what are the majority labels in this leaf node? In this leaf node, I have 100% blue, which is churn. Therefore, this condition, whatever condition went from the root node to this leaf node, that condition can be used as a classifier for not churn, or I'm sorry, churn, not churn, churn can be used for churn. Similarly, whatever condition went from the root node to this leaf node, for example, right, amount less than equal to 2032 and amount less than equal to 1770, right? So there are two conditions need to be satisfied here from the root node to this leaf node. So whoever satisfies these two conditions, we will say, okay, they are not going to churn. And what about this? This is still a decision node. So you can, of course, continue splitting it. Okay. And this is a point which is going to come up a little later. Okay. The one thing to understand is that this is the way in which the decision tree is built. Okay. That does not mean that in practical usage that every time we build the decision trees till 100% purity. Usually that is not done. And by now, I think all of us understand maybe why not, right? Because it leads to something called overfitting, right? So if you allow the tree to build fully all the time for any data set, it will overfit. So usually it is not done. And if you don't let the tree build fully, then you are going to get some impure nodes, which you have to stop and say, okay, I will call this my leaf node. But if you call an impure node a leaf node, suppose you stop this node, okay, this orange node. Suppose I say no, After level 2, I don't want any more tree. Then how do I put label on this node? This node has 2 red, which is 2 no churn, and 1 blue, 1 churn customer. The data tells me that 66% of this node is not churning. So I can go with a majority process. Say, okay, the majority is not churn in here. Therefore, I will label the whole thing as, the whole leaf node as not churn. Okay. So this is a point we'll explore a little in deep later. Okay. And if there is a tie, it's just going to be a random selection. Okay. If there is 2 blue and 2 red, you just call it red or blue. Okay. We'll see this a little later. But generally, this is how the decision tree is built. Now, this is the full tree, I think, the unrestricted tree for the 10 data points. So you can see here that this is my root node. It has all my 10 data points. Amount less than equal to 2032 goes this way. If you're not satisfied that condition, it goes this way. There is a pure node here. This is a decision node. Again, amount less than equal to 1770 creates this grouping here. And if that condition is false, you go here. And then there is another condition, amount less than equal to 1881 or more than 1881, right? So then that gives me these 2 leaf nodes. And this is essentially the end of the training phase. Okay, so this is the complete decision tree for the 10 data points using single feature. Okay, remember, at every decision split, it's only amount. Amount is being used to split the data space or the root node into various subregions based on conditions. Now, the general representation is like this. Okay, you will find the condition and some other information inside the boxes, and left side is generally considered as true. So if there's a condition and that is satisfied by a data point, you have to go left. If the condition is not satisfied, you go right. This is general convention. Okay. And you will see, for example, all the leaf nodes, wherever you stop it, you will see that how many data points are there. And if you total it, it has to give me my original data. So 3 plus 1 plus 2 plus 4 should be 10. You can check it out, right? 3 plus 1 is 4, plus 2, 6, plus 4, 10. So what you have essentially done, you've taken the data space and you've chunked it into pieces based on very, very simple linear conditions. Okay, series of linear conditions, and you chunked it into pure or homogeneous chunks based on simple linear conditions. So I think we can all appreciate, what a simplistic idea. It's a very, very simple idea, right? Nothing complicated at all. Simple idea. So it's a very interesting and powerful algorithm. Yes. Anyway, so in most representations, people will generally not show the true or false. It is understood that we understand left is true, right is false. So some representation may not show that, but generally left is true and right is false. And you can always check that. You can understand what's going on in the tree and check that, but generally left is true, right is false. Okay. So this is the actual Sklearn output. Okay. So I went ahead and fit a decision tree to my 10 coffee data points, and it optimized and gave me these values. Now, if you're wondering where I got these values from, 2032, 1770, 1881, how I got these values, I got it from Sklearn, right? So I'll tell you how the algorithm gets these values. So this is the optimal tree according to Scikit-learn, according to the decision tree algorithm. What I showed you is the model. Soon we will see what is the loss function, the objective function, or the cost function. Correct? We all understand that there is a cost function which gives the direction to the model building, right? What should my parameters be? Now, if you see here, these are the parameters: 2032, 1770, 1881. These are the parameters of the model. Okay. Amount also you should include. So amount less than equal to 2032, that's one parameter. Amount less than equal to 1770 is another parameter. Amount less than equal to 188, another parameter. So the model has optimized using some cost function and logic to give these values. Okay. Anyway, so this is exactly the same tree that I have showed you: 3 red points, 1 blue point, and all that. So you can see here 3, 0, which means 3 red points and 0 blue points. Here you can see 0, 1, 0 red point and 1 blue point, so on and so forth. It is also giving you the total number of points. So just above the list, the list, you can see the total number of data points in each node. It shows the leaf node also, it shows the decision node also, it shows the root node also. And you can see root node is white, okay. And generally you will see that the leaf nodes are slightly more saturated color. In simple language, say it's a darker color, right? So this is darker blue, this is dark orange, but this is not very dark. Why? Intuitively, I think we all understand why, because it's a mixture. The purer it is, the darker the color is, right? But we'll see that also in more detail. There is one piece of information here which I have not shown here, right? So I showed you this decision tree. Here, Sklearn output, there is one extra piece of information. So I am talking about these values. Let me just erase the unnecessary things. Yeah. So here, if you see, there is 0.5. Here, if you see, there is 0.278. Here it is 0. Here it is 0. Here it is 0. Here it is 0. And here it is 0.444. Notice that all the pure nodes are having the same value 0. Right? All the pure nodes are having value 0. That should give you some hint that this 0 may be a measure of impurity. First, we'll see how it's used for classification, then we'll go for the loss function. Okay. Yeah. So, okay, I built my tree. Okay, I built my tree. This is my tree. Okay, all you have to do is you have to follow the conditions, right? The tree is already built. Okay, tree is already built. At this stage, if a new data point comes, we just need to see what condition is this new data point satisfying. According to my tree, if amount is less than equal to 2032, I should go to the left. Correct? The amount for this new data point is 2197, which is greater than 2032. So I have to go to the right. So from root node, I have to go right. Any more conditions? No. We have stopped at a leaf node. Now this leaf node is a blue leaf node, and I've given the index here, the legend, sorry. So blue means yes churn, right? So already four churn customers are there. In my training data, I have 4 churn customers in this leaf node. Yep, not churn. That's right. So you start at the root node. Okay. Is 1654 less than 2032? Yes. Okay. Go to the left. Is 1654 less than 1770? Yes. Again, go to the left. Okay. So since 1654 is less than 2032, go to the left. Okay, most of you are saying churn. Let's just follow the route. Okay, is 1790 less than 2032? Yes. Is 1790 less than or equal to 1770? By the way, less than or equal to. Okay, I'm assuming we all understand this. I'm just saying less than, more than because it is simple to say. But the actual mathematical condition is less than equal to. Okay, so just keep that in mind. The opposite of less than equal to is greater. Okay. So $200 per month. This is my fees. Red means subscribe, that is continue, and blue means unsubscribe. So 200 is less than 300, greater than 100, greater than 150. So I go here, and red means continue. That's right. The answer is continue. Great. Now, one thing that I mentioned before was, see, you need not build your tree till all leaf nodes are pure. Generally, we don't do that because that leads to overfitting. Overfitting, very obvious. Like, see this, I have a leaf node with one data point. Just because one person in that root churned, can I say my new customer is going to churn? No. Like, see, if suppose, the amount is 1,800. Okay, so you come here, you come here, you come here, you come to this leaf node. Now this leaf node has one person in it. Just because one person in my previous year churned inside this leaf node, can a similar person, I can say, there's a high probability to churn. So these kinds of problems is what the decision tree faces, overfitting. So generally, what do? Generally, we don't allow this, right? Generally, we don't allow, leaf nodes to be so pure. Okay. And generally, we don't allow the tree to keep, building forever. So we have to cut the building somewhere. Now, suppose if you cut the growth of the tree somewhere, what's going to happen? You're going to get impure leaf nodes, right? See on the right side, you have 4 blue points and 2 red points. And see on this, we have 3 red points and 2 blue points. Notice that I have labeled this left side as red right? Just because there are 3 red points, and this right side leaf node I have labeled as blue because there are 4 red points. Actually, how that happens, you have to find the probability from the leaf node. So for this red leaf node on the left side, the red probability is 3 divided by 5, correct? So out of all the points there, 3 plus 2, right? 3 red and 2 blue. 3 by 5 is the probability for red, 2 by 5 is the probability for blue. Therefore, there's a higher probability for red. Therefore, I label it red. Same way, on the right side, the probability for blue is 4 by 6 and the probability for red is 2 by 6. Since the 4 by 6 is greater probability, therefore I will label that leaf node as blue, which means yes churn. Okay, so this is the general procedure. Trees need not have perfectly pure leaf nodes. Only the majority is required. Okay. Classification works in the same way. Once you label it based on the probability, classification works on the same way. In fact, we should all remember back to logistic regression, which also calculates probabilities, right? The machine learning model does not come to you and say, English word churn, no churn, or shows you color blue, red. No, it is throwing out probabilities. We are the ones who are interpreting that probability and saying, okay, there's a higher probability of churn in this leaf node. Therefore, I will label the leaf node as churn. Labels come from us. Okay. Machine learning models, they give you the probability. They stop at probability. We interpret and give the label. Okay. Anyway, so generally that's what we do. Now, how do we have impure leaf nodes in a tree? Very simple. Generally, we do hyperparameter tuning. Okay, everyone says unsubscribe. 125, so 300 goes here, 100, 125, yeah, blue is unsubscribe, correct, great. Okay, so what have we learned until now? We have learned that decision trees divide data space into more homogeneous or pure groups. That is how it is doing this classification. The final tree can be used for classification using the pathways, the series of the linear conditions, and the majority proportion in the leaf node. Whichever leaf node you are, see the majority. If we don't stop the tree growth, it will keep dividing till you have, very, very, very small pure leaf nodes, which is very bad overfitting. Okay. So that's exactly what will happen if you don't control the growth of the tree. This is what we've learned. What is the next step? What should we learn? Some of the important questions. How to define purity or homogeneity? What is this thing? Okay. What is the best split to choose at each level? We didn't address this. Can we use more than one feature in the tree? We did not see that. Can we use categorical features in the tree? We have not seen that example. Can we use the tree for multi-class classification? We have not seen that also. So let's go ahead and tackle all these questions right now. So decision tree is using multiple features. Okay. So suppose, please see on the right hand side. Okay. I have now 2 features. I have age and I have amount. Okay. The target is still the same. I want to predict whether my customers are churning or not. So a quick scatter plot just to see, what my data looks like. So this scatter plot has 3 pieces of information. I hope you can all appreciate that. X-axis is showing amount, 1 piece of information. Y-axis is showing age, another piece of information. And labeling is a 3rd piece of information. So all the 3 features I have on this scatter plot. Okay. And the idea is again the same, right? The idea is the same. You want a series of linear conditions that divide this data space into more homogeneous subregions. So this is my root node, right? My root node has 5 blue and 5 red. Okay. What is the next step? The next step is to choose a decision split. But now you have 2 choices. You have amount, you have age. Suppose that I go with the same. Okay. Suppose I go with the same amount less than equal to 2032. Then what's going to happen? Please look at the graph. You're going to divide the subregion on the left and the right side in this way, right? So on the right, you have 1, 2, 3, 4 blue points. That is what I've shown here. And on the left, you have 1, 2, 3, 4, 5 red points and 1 blue point, which is what is here. Okay. Now, this is a decision split node again, 1 blue, 5 red. So let's split it again. This time, let us use age as a split and not amount. On the graph, visually, what does it look like? It looks like a horizontal line because your age is actually on the y-axis. So age less than 29.5. Now, obviously, age less than 29.5 means down this way. And there's only 1 blue point here, which is here. And of course the false condition is age more than 29.5, and these are the 5 red data points that you will get in this subregion which I'm showing here. Okay, so now you have a yes region, you have no region. Okay, notice that visualization is easy up until 2D, okay, maybe even 3D. Okay, you can have 3-dimensional visualization on the screen, right? But after 3D, how are you going to visualize this? The idea is very clear though. The idea is very clear. You have this, and just imagine the space, 3D space. Just imagine the 3D space. Okay, take cuboidal chunks, or what do you call it, cube chunks, and just chunk this 3D space into small cubes. Just give label to each cube. That's all it's doing. In 2-dimension also, that's all it's doing. It's chunking it into these rectangular pieces and it is giving labels. Okay, so I can actually extend this and extend this. Okay, it has all these rectangles, so the rectangular subregions, you give labels. Great. Now how did I choose amount first, age next? So actually there's no discrimination between age and amount. Okay, there is a way for the decision tree to find out the best split, which we will see soon. What is the way to choose the best split? And that method to choose the best split is agnostic, independent of the variable. It doesn't care whether age is better than amount or amount is better than age, as per the meaning in which we understand. It will actually check all the possible splits. It will check vertical split, it will check horizontal split, it will check all the splits, and it will see which is the best starting split. Okay, so we'll see that in a little bit. My point here is that the decision tree is very easy to understand once you can imagine that, okay, all that's happening to my data spaces, it is being cut into pieces. Let's quickly deal with some small matters such as categorical features, and then we'll go on. Okay, so categorical features, no problem for decision tree. You know what, this is the thing, right? This is why decision trees were explored, and now it's such a powerful algorithm. In fact, all of you may have even heard of random forests, right, which is one of the most powerful machine learning algorithm models available, which we will do in the next session, random forest, which is built on decision trees, by the way. See how easily it handles categorical features. I mean, just it's too easy, right? Just create a dummy variable. So suppose you have gender. Gender is categorical. Category is male and female. Okay. Create dummy. So now you have dummy male equal to 1, right? I hope you all remember dummy variables. Each category will become its own column. There is a male column, there's a female column. Where male is true, there is a 1. Where female is true, there is a 1, and others will all be 0. One hot encoding. Okay, so create a dummy male equal to 1 for gender male and male equal to 0 for gender female. Simple. Okay, the condition in the tree will be very simple: male less than equal to 0.5. Now if what is meaning of male less than equal to 0.5? 0. And male 0 means what? Female. So if female, go left. That's all this means. If female, go left. And what is false for male less than equal to 0.5? Male greater than 0.5. What is that? Male equal to 1. And male equal to 1 means what? Your gender was male. So if male, go right. If female, go left. So quickly and simply it has encoded. Okay, it's as simple as that. And generally what we do in decision trees, we don't drop the additional dummy. Okay, there's a reason for that. Generally we want to give the tree more option to choose whichever split it wants to choose. We want to give it more options. If you remove the column, right, so you have a male column, you have female column, it will look like this: 1 0 1 0 0 1, whatever it is, right? These are the 2 dummy columns. Generally in linear regression or something, I will drop, right? I will drop one column, one of these, because it has same information. Where it's 1, it's 0. Where it's 0, it's 1. So it has the same information. We have correlation problems and things like that in linear regression, right? And even in logistic, we have same correlation issues and things like that. Decision tree, no problem. You keep both. It will go ahead and choose whichever helps it to build the best tree. So generally we keep both, all the dummy variables. Anyway, what does the output look? This is exactly how it's going to look. So the tree, same tree, by the way, for the 10 coffee data points. Interestingly, each time the root node split is the same. Okay, please observe 2032. So It's always thinking that amount is the best to split. Anyway, so the first root node split at 2032, and then you come down, you have this thing called gender male. Gender male less than equal to 0.5. Simple. So if your new customer is male, then gender male should be 1. So you go right side. If your new customer is female, gender male will be 0, which is less than 0.5. You go left. As simple as that. That's all. Categorical variables handled. Okay. Okay. So what have we learned until now? We've learned that decision trees using multiple features work the same way that they do for single feature. No discrimination between features. Just search the best split. How the best split, that we'll see. But essentially just search the best split. Check amount, check gender, check age, check every feature you're using. Look for the best split at a certain node and then split. Okay. Categorical features, what you do? Just convert to dummy and use it like any other numerical feature. That's all. We have seen this. Now what is still unaddressed? These questions. What is this homogeneity thing? How does the best split choice happen? And can we do multiclass? Okay. And I believe this is the time to start introducing the cost function, so to speak, right? The objective function, which is the measure of the impurity. Okay. Traditionally and most commonly, the Gini index is something that is used in classification cases as the loss function, okay, or the objective function. So basically in classification case, there are many metrics which try to capture the same effect. Okay, so what you noticed as when you went from the top of the tree and then you kept going downwards, what you notice is that the impurity level decreases and the purity level increases. Okay, let's actually look at this tree. So here, assuming that the 0.5 is a measure of impurity, see the next level. Just see both nodes in the next level. Here on the blue leaf node, the impurity is 0. On the orange decision node, impurity is 0.278. So impurity has decreased. Okay, impurity has decreased. Generally, that is the trend. Now here from you go from here to here, right? It goes back to 0.5 because now you have 1, right? You have one blue and one red, and then again it tries to decrease that impurity, right? So general trend is to increase purity as the tree is built. General trend is like that. Okay, so therefore we need a measure for this impurity. Now there are many ways to measure and capture the same effect. One is the misclassification error, right? So how many data points is wrongly classified. Another thing is something called heterogeneity or impurity. Typically we use something called the Gini index to measure this. There is also the concept of entropy, which is a measure of the non-constancy of a group, right? If there's more variation in the group, there will be more entropy essentially. But all these metrics capture the same effect. The goal is to reduce this error as the tree is being built. Okay, so the information gain should increase, the error should decrease. Okay, so let's quickly understand the Gini index. Suppose I have a decision node. So on your screen you can see orange color box, you can see 2 red and 3 blue. Okay, for now we'll forget churn, no churn. I think red blue is easy to talk about. So we have these 5 data points. Okay, how will you tell me how impure this group is? How can you tell me how impure this group is? So one of those metrics is the Gini metric, and the formula is given here. So the formula may look very weird in the beginning, but it will start to make a lot of sense once we understand it. So essentially it's you take the proportion or the probability of red and you square it, take the probability of blue and you square it, add these two things and then subtract from 1. Okay, what effect does this achieve? So let us try for this orange one. So I can see 2 red and 3 blue. So my probabilities are what? 2 by 5 and 3 by 5, correct? And this is exactly what I've written here, n red by n and n blue by n. Okay, so you put those things here, 2 by 5, 3 by 5, and now you square and add. Right, now you get what? 4 by 25 plus 9 by 25, 13 by 25. So you subtract from 1, you get 12 by 25 and you're getting 0.48. Notice and remember, in the decision trees that you saw before. For pure nodes, the value that we saw was 0, and for perfectly balanced nodes, we saw 0.5. The root node was 0.5. 2 and 3, right? 2 red and 3 blue. And what was the Gini index here? 0.48. Almost impure, but slightly in the favor of blue, which is why it is slightly less than 0.5, right? So all Gini index for binary classification goes from 0 to 0.5. That was the point of this whole exercise, okay guys? And that's the point of this graph also, okay? So here, if you see the behavior of Gini index, this is how it behaves. You choose a particular class, say red or blue, right? You choose any particular class and put it on the x-axis. So the probability or proportion of, say, red class or whatever, that probability can range from 0 to 1, correct? That probability ranges from 0 to 1. So when the probability of red is 0, that means probability of blue is 100, which is pure. In that case, the Gini index value is 0. If probability of red is 1, that means probability of B is 0 and red is 1. We just saw the answer to that. The Gini index is also 0. As you increase the balance in the proportion between the classes from both sides, it will maximize at 0.5. So when the probability, and by the way, if we use the probability language, it will make even more sense. If I come to you and say, I have a box with 2 red balls and 2 blue balls, the probability of getting red or blue is half. Are you confident if you pick a ball, you know you're going to get blue or red? Are you confident? No, you're not confident. If I come to you and say, I have a box, it has 99 blue balls, 1 red ball. You pick a ball, it should be blue. You are very confident. How confident are you? 99 by 100. You are 99% confident. That is the point of Gini index, right? When it is 50-50, I don't even know what's going to come out. That is the point. So when your proportions are the same, you will maximize at 0.5, highest impurity. Okay, wonderful. Take some time to digest this, right, and play with it, experiment a little later, right, and even you can check out the other metrics. But yeah, I think we are all getting a sense for the impurity business. Initially, it can be a little hard to grasp, I know, but it's intuitive enough, right? So in binary case, the maximum is 0.5. For multiclass, you will get slightly different value, but the behavior is the same. All right. Okay, so now let's go back to our original data set. Okay, this is my original data set. So the question is not just how good node is. The question is also how to choose the split. How do you choose the split? That's the main question, right? So let's go to that question. So this is my parent node, right? Or the root node. I'm not turning my video off, but I think the axis, we remember, I think it's amount. Let's just check it. Yeah, so this is the single feature amount. Okay, so I have all my data points here. So now what is the Gini of the root node without any split? Just apply the Gini formula. I have 5 red data points, 5 blue data points. We already know 5 equal. It should give me 0.5 maximum impurity, correct? So you put it in the formula and check for yourself. 5 by 10 square 1 by 2, 5 by 10 square 1 by 2, square it 1 by 4. So you have 1 by 4 plus 1 by 4 here. 1 minus half is 0.5. So the Gini of my parent node in the coffee dataset case is 0.5. Now we will go back and look at a scikit-learn output. Notice the value here. Okay, the root node, which has all my 10 data points, 5 plus 5, the Gini index you can see is written here 0.5. All right. So the root node in our case for the coffee data set 5 plus 5, the root node has Gini of 0.5. Now the question is, okay, how do you choose a split? Okay. Now suppose I choose this 2250. Okay, random split. Okay. Suppose I choose a split between these two blue points. Now one thing we need to keep in mind here. I don't need to check infinite splits, right? If anyone is kind of thinking, oh, I need to check infinite times. No, I don't need to check infinite times. In this case, I have 10 data points. how many combinations of subregions can I have? I just need to put a line between every two consecutive data points. That's all, right? I need to put one line between the first two data points and then say left and right. That's all. And then I move the splitting line to the next two data points, and then again I say left and right. Keep moving this between every two data points. How many such lines, how many such split will exist for 10 data points? Think about it. 9, right? You will get 9 such unique splits. That's all. You have 9 possible subregion splits from these 10 data points using a single feature. Of course, when you use more feature, you're going to have many more check, right? You have to search through many more splits, but it is finite. Even if it is large, it is finite. Okay, so here I need to check 9 splits. All right, now you can also ask within the split, right? Within like these two data points, within these two, I can move my split to any real number. There are infinite real numbers. Therefore, I am checking infinite times. No. Why? How does it matter? Just take the midpoint. That's all. Just take the midpoint of the two data points. End of story. Left region, right region. Okay. So, how many possible splits are there in the actual algorithm? 9. For 10 data points in one axis, only 9 possible splits. Now, out of those 9 possible splits, let us just randomly choose one of these splits as 2250. Okay, so I have my amount on the x-axis. I have all the values, data points. I'm randomly choosing 2250. Quickly, we can find Gini index of left and right. Very simple. Let's just do that, right? There are two subregions, left and right. Let's check. So on the left side, what is happening? 1, 2, 3, 4, 5, 6, 7, 8 data points. And on the right side, 1, 2 data points. Forget the right side. Left side, let's check. 8 data points. So the denominator is 8. We know how to find Gini of the left group. Denominator is 8. 5 red, 3 blue. So 5 by 8, 3 by 8. That is exactly what is shown here. Square it, calculate the Gini. You will get around 0.47 for the left subregion. For the right subregion, you don't even need to calculate. By now, you should know, right? This subregion is pure. There are only 2 blue data points in the subregion. So what is the Gini for that? 0. Okay. So what? How do you calculate the Gini of the split? Right now you can say, I showed you the left side Gini and the right side Gini, but how to combine this? How to combine this and say, did I do a good job in splitting or not? Right? I need a way to compare this with the parent node Gini. And what was the parent node Gini? Remember, 0.5. And this also should be obvious. 5, 5. Correct? 5 blue, 5 red. So the parent node Gini is 0.5. And for 2250, left side is 0.47, right side is 0. How to compare the result with the parent? All we have to do is take a weighted average. That's all. So look at the table here. The original data space, the Gini is 0.5, and it consists all the 10 data points, 10 out of 10. Okay. So the actual Gini of the parent node is 0.5. We know that. The left subregion, amount less than 2250, we calculated the Gini as 0.47. The right subregion, amount greater than 2250, we saw that the Gini is 0. Find the weightage according to the parent. So the left subregion has 8 data points. So the weightage is 8 out of 10. Correct? And the right subregion has 2 data points. So the weightage is 2 by 10. All you need to do is now find the weighted average of the resulting Ginis. So the formula is weight left into Gini left plus weight right into Gini right. That's all. 8 by 10 into 0.47 plus 2 by 10 into 0. And this will give you 0.38. So this is how we define the Gini of a split. Okay. And we use the term Gini of a split. It's somewhat, like not so technical. Technically, what I'm calculating here is the weighted average of the Gini of the resultant subregion of a split. But who will use so many words, right? Therefore, we just call it Gini of the split. Okay. So the Gini of this 2250 split is 0.38. Now you compare 0.38 with 0.5. it is less. Impurity has generally reduced. Therefore, this is a good split. Okay, the impurity value has reduced. Therefore, it's a good split. But if you remember the scikit-learn, when I fit these 10 data points to my decision tree in Python, it considered 2032. So basically, what did it do? It considered one split here. It found the resultant Gini. Then it considered the next split between the next two data points and then found the resultant Gini. Then, it kept on going like that. So somewhere in between, it found 2032 as a value. I think it was here, right? I think somewhere here. So 4 blue points and 6 points on the left side with 5 red. So 2032 is there. So I'm saying 2250 is a good split. Is 2032 better or worse? Of course, it should be better, right? I mean, Python optimized it to 2032, so it should be better. Let's check that. Let's actually check that, right? So suppose you consider now the 2032 split. Right side, no doubt. Blue, 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 blue. 4 blue. Pure, 0, right? We know that. The Gini of the right side is 0. Left side, now you have 6 data points, out of which 5 are red, 1 is blue. Right? So now you put those probability values, 5 by 6, 1 by 6, square it, calculate the Gini, and in the end you will get 0.28. If you do the calculation, 26 by 30, 1 minus 26 by 36, whatever, right? You will get 0.28. The story is not over. Now you need to calculate the weighted average. So what is the weightage this time? 6 out of 10 for the left, 4 out of 10 for the right. The left Gini is 0.28. The right Gini is 0, correct? Therefore, you multiply, weight of left into Gini of left, that is 6 divided by 10, the left side weight, times the Gini of the left subregion, which is 0.28, we just calculated. And the right side weightage is 4 by 10, right? And the right side Gini is 0. So when you do all this calculation, you will get 0.17. Now, what was the value at 2250? 0.3828 something, 0.38. So from 0.5 impurity, you went to 0.38 at 2250 split. At the 2032 split, you went from 0.5 to 0.17. So the impurity has reduced way more, right? This is a much better split. Again, think of the objective of the decision tree. It wants to divide the data space into more purer groups for better classification, correct? So the impurity should reduce as much as possible. This is how the best split for a node is chosen. It checks all the possible finite splits in this way and then chooses the maximum decrease or maximum change, call it what you want, maximum difference in the impurity value, the Gini value. So 2032 is a much better split. In fact, it is the best available split for the root node with one feature. Okay, it is the best available split out of all the split checks. In this case, 9 times it will check for the 10 data points. You just take the midpoints, right? Of all those splits, this is the best available split. Therefore, the root node will split with this condition. Okay, yeah, and that's how the splitting works. So essentially, you check each and every possible split in that level using all available features. Here I am showing you only amount, but if you have amount and age, it will check all the splits. It will check the amount split also, it will check the age split also, it will check each and every available split, and in each of those splits you will get 2 regions, right? And for each of those splits it will calculate this Gini. Okay, so this is what I've written here. Remember that each potential split result in 2 regions. We cannot check for infinite values. We should not also. So we just use the midpoints between the data points. It's a very simple and fair method to do that. If there are multiple features, just check all the features. There's no discrimination between age, nothing, right? Just check all the possible splits, all the possible age midpoints, all the possible amount midpoints, all the possible gender midpoints. There's only one, right? Gender midpoint. So just check everything and see the resultant split Gini. That's all. And for this specific data set, amount less than equal to 2032 seems to be the best starting split. Okay, I think even if you use all the features, the best resultant grouping comes from amount less than 2032. Okay, so after that, what's going to happen? After that, exact same thing will be repeated for each subregion. That's all. Anyway, so we've answered a lot of questions. We've answered what is a good, how to measure impurity. We've answered what's a good split, what's a bad split. We answered categorical variables. We answered multiple features, right? The only thing we haven't answered is multiclass, right? So how does multiclass work? So technically speaking, it's more or less the same concept. Okay, class labeling will slightly change, but the logic is the same, majority. So when I say class label, I mean leaf nodes, right? And Gini formula will slightly change, but exact same behavior and intuition. Okay, so what just to give an example for the classes, suppose I have now 3 categories of my target variable. Okay, red, blue, green. So if you see this node on the top, I have 3 blue, 1 red, 1 green. Probability of blue is highest, 3 divided by 5. So now you have 3 probability values, 3 by 5, 1 by 5, 1 by 5. So quickly, if I can just go back to some decision tree where here it is. So if you see here, right, this is the case of the coffee data set, correct? This is churn, and churn was having a binary value, correct? Yes churn, no churn. It was a binary value. So therefore, the number of elements in that list will be 2. So here you have 5, 5. See this list 5, 1. See this list 0, 4. This list 4, 0. So in each of the nodes, it is showing you how many training data points are there. From that, you can get the probability. So this is very orange looking. So must be the red class, whatever. The red class probability is 5 divided by 6. Okay, 5, 1. Correct. So in my slides, I was showing you the data points using the dots, right? In all of the decision trees initially, I was showing it using the dots, correct? The data points. But then later I told you that generally what is shown in the decision tree is the number. So if you see the leaf nodes and everything, the number of the training data points will be shown. So in this Sklearn output also, you can see the same thing. The numbers are shown. So 5 red, 5 blue. And here I have 5 red, 1 blue, so on and so forth. So in a 2 category case, you will find 2 numbers in the list. In 3, you will find 3. That's how multiclass works. Okay. So going back to our multiclass slide, very sorry for going back and forth like this, but yeah, it's I think it helps to compare. So in this case, my target variable has 3 categories: red, blue, green. It could be yes, no, maybe. Okay, just saying. The different use cases will have different categories. So 3 by 5 is the highest probability. Therefore, this leaf node will be labeled as blue. In this case, again, I have 3 red, the other ones have lower probability, so I will label it as red. In this case, in the third case, I have 2 red, 2 green, 1 blue. Blue, of course, not happening, right? But 2 red and 2 green, which are both equal. So same logic, randomly choose. And even in the binary case, it randomly chooses. If your leaf node has exact same number of red and blue, it chooses randomly. Okay. So in this case, because I have 2 by 5 probability of red and 2 by 5 probability of green, it will randomly choose between the two. So basically, it's the same majority rule. Okay. And what is the difference in the Gini index? Absolutely nothing. You just have one more data point, one more category. So initially for our binary case, it was n red by n and blue by n square, right? Now you just add one more term, n green by n square. That's all. And why the square is there? For same reason. If you remove the square, total is 1. So Gini equal to 0 always, which is no use. And we have seen with the square, it has a very beautiful, shape. It has a very beautiful meaning. 0.5, right? Gini 0.5 means I don't know what's going on, right? It could be A, it could be B. But if Gini is closer to 0, then it is a pure node, right? Same logic. So I encourage you all to, explore multiclass and all of these things a little bit further, right? So what have we learned until now? We need a measure of impurity, okay, to make the decision tree work. And generally, this thing called Gini index is quite commonly used, although people do use entropy also. right? So there are different criteria you can use, but they aim for the same thing. They aim for more purity as you go down the tree. Gini for a pure node is 0, Gini for impure node is 0.5, for binary case, for tertiary case it is 0.67. You can get these values using the formula, so on and so forth. Okay, so Gini in the binary case ranges from 0 to 0.5, 0.5 being the most impure and 0 being the most pure, everything else in between. Okay, so this Gini is used to decide what is a good split and what is not a good split. Okay, and the tree grows using the split comparisons from child to parent, as in from parent to child, but compares the child Gini to the parent one, right? And within a data subspace, what the tree does, it searches for all the possible splits, calculates all the possible resultant Gini, and selects the best one to split again. Okay, and multi-class trees work more or less, and in fact exactly the same way. Okay, so quick summary: decision trees are, a set of sequential conditions on the input features of a data set. Okay, and these sets of conditions, series of linear conditions, divide the input space into, I like to say, rectangular pieces. The term used is regions. The linear set of linear conditions divides the input space into regions. Each region is then assigned a class label as an output if you declare it as a leaf node. Okay, a new data point can then be classified which region it is inside. That's all, right? Which region it is falling in. How to find out which region? Follow the conditions, right? To determine the region, you just follow the set of conditions that make up the tree. And conditions for the split are determined using Gini or an equivalent impurity measure. Now, quick comparison of advantage, disadvantage. See, we've seen the advantage. The tree is very easy to understand and interpret, right? It is so easy, right? It's just telling me the conditions that lead to somebody churning or not churning, for example. It doesn't really need any data preprocessing. If you noticed, I did not scale my data. I didn't do any such thing, right? I didn't scale data. I didn't do anything like that. I did not even care about outliers. Interestingly enough, the decision tree is very robust to outlier and missing value impact. Okay, because it doesn't calculate distances at all, right? If you see linear regression, right, it calculates distance. So the line slope will be affected by outliers, linear and logistic, right? Outliers will affect. Decision trees are not affected that much by outliers. Doesn't even need rescaling. And essentially it is handling nonlinear relationships. If you remember two graphs which I showed in the beginning, one was a nonlinear curve like this and the other one was a rectangle like this. Both are achieving the same thing. Okay, so if you see, both are actually creating the boundary, outside and inside boundary, right? And this is nothing but a set of simple linear conditions. This thing, it may be some kind of complex formula, correct? On the left side, it's a complex curve. So it's handling nonlinear relationships pretty well, right? A set of linear conditions is handling nonlinear relationships pretty well. And there is also an implicit feature importance. I'll come to that. Maybe when we discuss the Python demo, we'll discuss more of feature importance. But basically, according to my 10 data points, all of you noticed the first split choice was always amount, correct? So according to the decision tree, amount is the most important feature. So there is an implicit hierarchy of feature importance also. Okay, all of this is done just by building the tree, right? In linear regression, everything you remember, I have to rescale, then I have to compare coefficient, then I have to regularize, all of that, right? We have to do all of that just to find out which features are good, which features are bad. Decision trees, the implicit feature importance, whatever features are above near the root node are important features, whatever features are below are less important features. It has implicit feature importance. Okay, now what are the disadvantages? Of course it is resource hungry. I showed you for 10 data points and one feature. We will be seeing for many tens of thousands of data points with 20 features, 30 features. Then just imagine the amount of time required. It is a search algorithm. Okay, it is essentially a search algorithm. So it is very resource hungry, computationally heavy. Uh, it is also sensitive to data changes. Basically, if I use 10,000 data points to build a tree, suppose I remove 100 data points. How many data points I have? 9,900. You will say almost the same. If I have a linear regression model, it will be almost the same. If I build a linear regression line for 10,000 data points or for 9,900 data points, how much it will change? How much will the line change? Very less. But the decision tree can look very different. Completely depends on the data. So if you use 10,000, you might find one tree. If you use 9,900 data points from the same data set, you might find slightly different. Okay, that's a slight disadvantage. And of course, we understand this, that if I don't restrict the tree growth, it is going to overfit. Okay. Now, regression using decision trees, I want to leave it as additional reading. Everything is more or less the same. Okay, the algorithm, everything looks the same. The only differences, the major differences I've written on the screen. One is in classification for a leaf node, I calculated probability, and based on probability, I gave the label name. So what is going on in the regression leaf node? Question number one. And in classification, I used Gini index to measure impurity, right? Whether my purity is increasing as I go down the tree is measured using Gini index, right? What is the criterion to be used in regression, decision tree regression? These are the two major questions. So I would like everyone to actually, study decision tree regression on their own. It's more or less almost the same. It's just these two things you need to try to figure out. Okay, what is the replacement from classification to regression? Quick discussion on the hyperparameters. If you remember in the agenda, I had written that we will discuss the hyperparameters. So we'll discuss some hyperparameters now, and then we'll explore further in the demo. Okay. So we'll do this hyperparameter discussion for 10 minutes. So as I said before also, if your decision tree if your algorithm is simple, then there are going to be many hyperparameters. So for all the good things that are offered by the decision tree, there are of course these issues that we need to deal with, overfitting especially. And there is a concept in the tree which is called pruning. And pruning, I mean, whoever has any interest in gardening, pruning means you cut those additional branches and leaves. Like when you have an actual plant or a tree, you cut leaves and branches, right? So that's called pruning. Same term is used for decision tree also. Basically, it is the cutting down of sub branches in the tree which are bad sub branches. Bad means they are leading to overfitting. So if you cut down some of these bad sub branches, you can encourage better generalization. Generalization means what? Let's remember, it means that the model performs well in any scenario. Given any new data, it should perform consistently and well, right? So this is the process of pruning. You just need to cut out some of these sub branches. How do you do that? There are many ways to do that, right? Classically, we divide this into two parts. One is pre-pruning and one is post-pruning. Pre-pruning is nothing but not allowing the tree to grow before the algorithm, right? So you set the hyperparameters before building the tree. So you don't allow some sub branches to grow. Okay, that is called truncation also. Post pruning means you allow the tree to grow fully, and then you use certain metrics to calculate which paths are complex and not useful, and then you collapse them. Okay, and some examples we will see. So maximum tree depth, this is I think the most obvious example, right? How many levels should I keep splitting my data space? This is a pre-pruning hyperparameter. Okay, so if you say 4, that means it will check for split 4 times. It will divide into subregion 4 times. If you say 8, it will go till the 8th level basically. Okay, and if you don't say anything, it is going to go on and on till you get pure leaf nodes. Okay, so generally this is not set by default. Okay, I believe the default is none. In Sklearn, it is none. So what will happen is that the tree will grow until all the leaf nodes are pure. We don't want this, right? This is not recommended because it leads to overfitting. You should definitely tune for this. And by the way, we will do some deeper hyperparameter tuning in the demo today. Uh, Too much tree depth generally leads to overfitting. Too less tree depth generally leads to underfitting. Okay. There's another hyperparameter, very interesting one. This is minimum samples for split. Basically, how populous should my leaf node be for me to split it? So basically, I'm asking the question: if my leaf node has 20 data points, or if my decision node, sorry, has 20 data points, then split it. If my decision node has less than 20 data points, don't split it. Okay. So now you are putting a condition on the size of the leaf nodes. Okay. This is also a pre-pruning hyperparameter. You set this value, then after that the tree cannot grow. Okay. So this is the minimum number of data points that must exist inside a decision node, not a leaf node, decision node. Okay. For it to be eligible for splitting. This is also a good hyperparameter. Okay. So now if this value is less, you will get smaller leaf node, correct? That leads to overfitting. If this value is more, you will get underfitting. All right. So this is another hyperparameter. Now this is an interesting hyperparameter. We won't go too much into detail of this, but this is a post pruning hyperparameter. It's called the cost complexity path alpha. And though it sounds daunting, it's essentially just identifying branches of the tree. After growing the full tree, it is identifying branches of the tree where it is too complex and it is not giving me good cost reduction. Cost reduction means what? Gene index. Okay, so it is analyzing paths which have too many input variables and very less change in the gene index. Okay, this is a post pruning hyperparameter. You build the tree fully, then you check all the sub branches. Okay, the default here is 0, which means no pruning. So this is also a popular hyperparameter to tune for. Basically, higher the value of this parameter, stronger or stricter the condition. Okay, that is more the number of nodes and branches that will be cut out. So more CCP alpha, more pruning. Okay, and less CCP alpha, less pruning. Default to 0. So we won't go into this in too much detail. I will of course leave this to the learners for additional reading. There are of course some other general hyperparameters. Okay, as I said, criterion you can use for splitting. Generally, the Scikit-learn default is Gini for classifier, but there are others such as entropy, which you can check. Right. Class weight is also a very interesting parameter because in this classifier we are so much influenced by the proportions of the churn, no churn, right? The class balance, right? You can set it to balanced if your class balance is bad. Okay, generally you can check also the documentation. What are the different values for class weight? Generally, if there is a lot of imbalance in the class, so suppose your training data has 90 churn and only 10 no churn, that's a class imbalance. So either you should introduce better class balance in your data set, or you should handle it using hyperparameters such as class weight. Okay, essentially it tries to balance out the number of training samples by setting weights inversely proportional. It's an optional sort of thing that you can use. And finally, just want to talk about one very interesting hyperparameter. We will not use this in decision tree, although it is there. Okay, but we will use this in further depth in random forest in the next session. Okay, this feature is called maximum features during split. This hyperparameter, sorry, it is called maximum features during split. It's a general hyperparameter. Basically, if you remember, whenever you go for the split of a decision node, you are checking all the possible splits using all the possible input features, correct? Now, if you set a value for this maximum features hyperparameter, then the decision tree will not check all the input features. That's the point. Okay, the default value is none. This means whenever there is a split, it will check all the possible features: amount, age, gender, whatever. Okay, but you can limit this searching space. For each split, you can limit the searching space. That is what this hyperparameter will do. The purpose is to discourage overfitting again, right? The purpose is to encourage randomness, discourage overfitting. Okay, it is a worthwhile hyperparameter. You can tune for it, but as I said, we will explore this in way more detail in random forest because it makes a lot of sense, much more sense there, I should say. Anyway, just an example. Suppose if I set max features to 3. Now all my features in my coffee data set are what? Gender, job, income, age, amount. What's going to happen if I set max feature to 3? It will randomly select 3 features from the 5. So for the root node, it may select gender, job, age. Now it will search only gender, job, age. It will not search income and amount. Okay. Then when you go to the next split, it will choose again random 3 from the 5. So this time job, income, age. So again, it will only search job, income, age, and then choose a split. So as you can see, it introduces some randomness and a little bit of blindness, right? You can think of this as blindness, right? Partial blindness to the training data. And if you remember linear regression, that's how we do generalization. That's how we do regularization, right? By limiting the exposure to the complete training data. Even in linear regression, that's what we did. We increased the alpha value to put penalty on the beta coefficients, correct? So it was like a weaker model, blinder model. Similar logic here. Okay. Yeah. So generally, there are some suggested values for this, like square root of total number of features. This is there from, I think, the creators of decision tree in their own paper. They suggested this square root of total number of features. So in the coffee data set, it is 1, 2, 3, 4, 5. Square root of 5 is what? Around 2, I think. So they suggested 2, right? Things like that. But as I said, it is generally implemented much better in association with random forest. So we'll not worry about this. Okay. Quickly just giving you a sneak peek into the documentation screenshot. You should explore the documentation in greater detail when you get the time. This is the decision tree classifier class from Scikit-learn. Okay. And as you can see, all the parameters and hyperparameters, not parameters, sorry, hyperparameters, criterion, some of these will not go into, right? There are a lot of hyperparameters, so you can check those. Criterion, maximum depth, minimum samples, this we spoke, right? Minimum samples leaf, that's like the other side. So minimum sample split means decision node, how big it should be for split. Minimum sample leaf means after split, how big should my leaf be? So that's the another hyperparameter, max features, so on and so forth. Okay. So again, I've divided this into meaningful parts, setup, and then we have unrestricted tree model, we have different restricted tree models. Okay. And then we have a bit of hyperparameter tuning. Okay. So part 1, setup. Let's start with this. What are we doing? We are loading packages for the exercise. We are loading the data. We are pre-processing the data, which is very less pre-processing. Okay. In decision trees, we're going to split the data into input and target. Remember, we are doing supervised learning, so split it into input and target. Again, remember, we are doing supervised learning, so we have to split into training, validation, and testing. We are doing hyperparameter tuning, so we need the validation set to understand what's a good hyperparameter value, and we will see all this. Okay. NumPy pandas, basic things, mathematical operations, data frame operations. Seaborn, matplotlib for visualization, right? Train test split from Sklearn. We have seen this for splitting the data. These are the main methods here. From sklearn.tree, import decision tree classifier. And this other thing is for visualization. I'll come to that. This is the main model. Okay, this is the class decision tree classifier. And we need some metrics to understand how our model is performing. Since it's a classification case, you must be aware of the confusion matrix and the accuracy score. Right. So this is the data that I'm using. Okay, telecom churn data. So it's like bigger version of my coffee data, right? So this is a very, very standard data set. In fact, I've given the Kaggle link here also. It's a very, very common and standard data set. So let me read it and have a look at it. So as you can see, these are the customer IDs, right? This is essentially a telecom company, and we are having information about the customers. Okay, so we have gender, whether they are male, female, whether they are senior citizen, what is their tenure with the subscription of the telecom, what kind, do they have phone service, do they have internet service, what kind of internet service, have they opted for online security. So all of these features, and there are 20 columns it seems, and 7043 customers. So all of these different features. Are they opted for streaming movies? Have they opted for streaming TV? What are their monthly charges for each customer? What is the total charges? Things like that. And the final column, churn, this is the column that we are interested in. All right. So the data set is here, and so data concerns a telecom company and their customers. Objective is essentially to predict which customer will continue with the subscription, which customer will churn out. So if you see in the churn column, we have continue, which means no churn, and then this customer has churned. They left the telecom subscription, right? So we want to predict, we want to classify that new customer, are they going to churn or are they going to not churn? Okay. So what kind of columns do we have? Gender, senior citizen. We just saw this, right? We saw these columns here. And what is the shape of the data? We saw this also, 7043 into 20. So I have 7043 rows and 20 columns. Info, this is important to check, null values, type of column, and all of those things. So I have a lot of categorical columns. I have some numerical columns, and churn, of course, it's categorical. 7043 rows, and then 7043 values for each column. So there is no missing value. I've also accompanied this with a data dictionary. You will get these files and everything at the end of the demonstration. I will share the link with you guys for the data, the dictionary, the PDF, everything. Okay, and the notebook. So these are the descriptions of the features. I just described them, so you can read these in your free time. And note that the churn feature is the target variable. Okay, so this is very fairly standard data set. For this demonstration, we'll use a subset. Again, the idea is to allow the learners to actually deal with the raw data set. So I would be using a subset. On top of that, if I use all the features, then the decision trees will build a little bit slowly, right? It may not be observable in decision trees, but in random forest, you will be able to observe how slow it is. Okay, so we'll use a subset here. These are the features I want to use: gender, senior citizen, dependent. Okay, tenure, phone service, payment method, monthly charges, and churn. Now I've taken the subset. Let's just quickly look at the data, what it looks like. So here I have gender, female, male, binary. Senior citizen already seems to be encoded 0 and 1. Dependents means, okay, I guess this is yes and no. Tenure, it must be the number of years. Phone service, whether they have phone service or not. Payment method, how are they paying for the subscription? So it seems to be not binary. It has many categories: electronic check, mail check, bank transfer. What are the customer's monthly charges? This must be in dollars, I believe. And whether the customer churned or not. Now, obviously, we need dummies for the categorical variables. Okay, and just remember one thing: in decision trees and random forests, we retain all the dummy variables, right? And till now, we have seen how decision tree works. Allow the decision tree to choose the best split. Okay, we don't need to worry about correlations and things like that. Okay. And finally, just one very interesting thing about Scikit-learn. If you have a target variable like churn, you don't need to create dummy for churn actually. Okay, in the binary case, I believe you don't really need the to make it 0 1. Okay, so it is capable of handling the categorical variable internally. So you don't need to create a dummy for churn. Although you can, nobody is stopping us. You can create a dummy for churn. When you create dummy for churn, you will get churn no, churn yes. Since you have to only have one target variable, just remove the churn no column. Keep the churn yes column, and the churn yes column will have 0, 0, 1, 0, 1, so on and so forth. Correct? So you can do that if you want, but for this case, you don't need to. Okay, if it is binary, I believe it should work without converting to 0 1. for the target. So let's create dummy variables for all the categorical features except churn. And by the way, if you notice here, I am not even specifying which are my categorical features, because pandas is able to understand that, right? In df info you already have which is object, which is not object. So object means categorical, correct? So you can just directly drop the churn column and get dummies. So now I have a dummy data frame, df dummy. Now because I drop churn, now if you just look at df dummy, it will not have the churn column. As you can see, here it does not have the churn column. You can see all the other categorical columns have been converted. It will also retain the integer columns, right? Correct. And it has the different dummy variables for the categorical. Now if you also check the parameter for get dummies, you will see drop first, the default is false. Okay, so in linear logistic you want to drop redundancy. In decision tree you don't want to drop, you keep the dummy, all the dummies. Okay, so we will use the default value of drop, which is false, which is why it is giving me both the dummies, gender female and then gender male. Okay, now of course churn is not there in this. So if you want to look at the full data frame, you can just concatenate using pd concat. You don't need to, because little further down the line, again we are splitting it, right? X and Y input output. But just for sake of completion, if I just want to look at my data set before I proceed with the machine learning, I can add the churn column back. Okay, and here you can see no yes, whatever. Not a necessary step, obviously, because you're splitting again into input output, right? So now what are my columns? These are my columns. I showed you that gender now has gender female, gender male. Dependent is now dependent no, dependent yes. Phone service no, phone service yes. And payment method has many categories. So bank transfer automatic, credit card automatic, electronic check, mail check. So 4 categories. This is what my columns look like. Okay, and this is what my data looks like. Great. Now I have all the features, all the splits, possible splits that I need, and I have my target. So the next step, it is to obviously split into X and Y. So df.dummy drop, df_dummy.drop, remove the churn from the column axis 1. So that's your input, and Y is nothing but the churn column. Okay. So now we will split it into 3 sets. Okay, we'll split into training, validation, and testing. So remember, training is used to find the right parameters, right? It optimizes the parameters, the split, correct? So we'll use training for that. Validation is used to check the trained model on the validation data and see how is the performance. And we have, if you remember, the performance should be good and consistent. That is what we mean by generalization, correct? And of course we can use the validation set to change different hyperparameters and see which is a better training. Okay, that's what validation is mainly used for. Testing we will use for declaring the final performance. Okay, so now you must have seen this code before. Train test split, my X and my Y, which are here. Okay, X and Y, which came from df dummy. And then I have I've kept 60%. Now I have lot of data. Basically I have what, 7,000 something rows, correct? So I am more than happy to use 60/40, right? 60% of 7,000, 4,000 something I will use for training, and remaining 40% will be around 2,800. That I will split half. So in the next train test split I have written 0.5 training size. So whatever is left from the 60% I will split into half. So essentially I'm doing 60/20/20. Okay, and remember that if you want to reproduce the results, you have to keep random state equal to 0. Okay, so these are the leftovers, by the way, X temp and Y temp. Okay, these are the leftovers. So these leftovers you put it in the next command of train test split. So here I'm getting X train and Y train 60%, and here I will get X validation, Y validation, which is 50% of the remaining 40%, right? Which is 20% of the original data set. Similarly, X test, Y test will be 50% of the remaining 40%. 1 minus 0.5 0.5. That's why. Okay. So as you can see, I have 4,200 data points in my training, 1,400 in validation, 1,400 in testing. So part 1 is done and we are ready to go to the tree. So let's look at the unrestricted tree model. Okay. So here, if you see, I told you this is the class that we will be using. So first we will create an instance of the class. So decision tree classifier, and you call the class. Okay. So this initializes the class. In fact, you should always check the documentations, correct? Of the class. You can of course press Shift Tab in Jupyter, or you can just open a documentation page. And here you can see the default criteria on Gini. Max depth is none, min sample split is 2. Like, look, these are all overfitting. You know, these are all perfect for overfitting, correct? Maximum tree depth, none. Okay, minimum samples for splitting, 2. So if 2 data points are there in a decision split, it will split. And minimum samples in leaf, 1. So if I just let it grow, the pure nodes, if required, will even be of size 1. So the unrestricted tree is made for overfitting. That's all I can say, right? By looking at these hyperparameters, this is made to overfit. So let's call it tree model 1 and let's fit it on the training data, X train, Y train. And as you can see, it is fit. Now see, here I have used this tree.plot tree. I would urge learners to study this method and maybe check. There are other substitute methods for this. Basically, if you remember, we imported this thing from Sklearn import tree. This tree is nothing but this tree, basically, right? So from Sklearn dot tree, as you can see, this module tree, that is exactly this module. Okay, there is another method in this module which is called plot tree. Sorry, not module, method. Yeah, method. So that plot tree method I'm using here. Okay, plot tree. So it essentially plots the tree. Okay, this is where I got all those trees from. And these are some additional parameters for this method to show the name of the features and things like that. Okay. Now I would draw your attention to this here. I have used max depth equal to 2. So let me run this first. Okay. As you can see, level 0, level 1, level 2. Okay. Now you can change this. You can of course, max depth equal to 1. It will show you only one split. Interestingly, in this case, the tree is saying that tenure is most important. Tenure is most important in deciding whether somebody churns out of the telecom subscription or not. Means if you're using it for a long time, something happened. So that's what is being said here, and we will look at the outputs and all that. And the problem with this, if I do not set max depth, suppose I just delete this and I press enter, see how much time it is taking. My cell is still running. Okay, it is still building the tree, and sometimes it could even crash. Okay, so just saying, sometimes if you have, and this is a subset, 7,000 data points and 5 to 6 features or something. As you can see, it is still building the tree, right? It's been 10 seconds almost, right? It is still building the tree. This is where you should be a little careful when you plot the trees. Okay, it may take a long time to plot the tree. In fact, when you're working with more sort of data, many tens of thousands data point, and many more features, then what is going to happen? As you can see, my code is still running. Okay, and I don't think I want to wait, so I'm going to interrupt this. As you can see, I have interrupted the call. Okay, yeah, I've interrupted the call, and that's because the tree is just way too big and it's almost taking too long to plot. So generally what we do is we limit the max depth to some amount, say 2, 3, whatever it is. Okay, great. We also said that the tree has implicit feature importance, right? So in fact, there is an attribute called feature importance, and how to access attributes. So once you fit your model, you put dot and you put tab. Like all of these, you will find the methods and the attributes of the object. So the class is decision tree classifier. The instance of the class is the object. So one object I have tree model 1. This object has lot of attributes and methods. So feel free to go through those. One of those attributes is feature importance. Now this is obviously not making sense, right? I just printed feature importance. What is all this? 0.037, 0.324. Not making sense, right? Actually, these are the importance values in the order of the original features. So if you go back to DF columns in the dummy, senior citizen, tenure, monthly charge, gender, female, in the same order you have these feature importance. So what you can do, you can just make an index, take the data from here. Okay, this feature importance array, you put it as the data in a data frame. So you just take the columns and you take the feature importance and you can build a data frame quickly to check. So tenure and monthly charges, these seem to be the top features, right? Monthly charges has a bit of more importance, it seems, and tenure is one of the more important features. So these two have a very high role to play in classifying whether somebody is unsubscribing from the telecom or not. So as you can see, all of these feature importance values you can easily analyze. So decision trees obviously can be used not just for machine learning modeling purpose, it is also used for analysis, right? So in the data analysis activities, you can use decision trees for analyzing the impact of various features on the target. The next thing that we need to understand is the confusion matrix. So there is a method that I think I imported from Sklearn. Yeah, sklearn.metrics. I have imported confusion matrix. I've imported confusion matrix display, and I've imported accuracy score. So first I'll display the confusion matrix. It looks nice, right? So confusion matrix display, and then from estimator, right? Use the from estimator method. I would again suggest learners to read this further. There are substitute methods. This is just we want to plot the confusion matrix, right? It's a heat map essentially. And then you give the model, and then you give the training data, you give the validation data. As you can see, I'm giving training data here, I'm giving validation data here. Here is the confusion matrix. So the training data, you can see, okay, so on the y-axis, you have the true label. That is whether the customer did not churn or churned in actuality. On the x-axis, you have the predicted. What did your model predict? So 20, for example, this 20, this is the case where the customer actually churned, but your model predicted that they did not churn. This is an error, correct? This 20 is an error. So as you can see, the error is very less, correct? Just check the actual. So no and no match is 3103, yes and yes match is 1102 out of 4200 something, correct? So almost 4200 it got correct. This is clear overfitting. You can see from the confusion matrix itself, clear overfitting. And in the validation, you have a lot more errors. As you can see, 185 cases it predicted yes, where actually it was no, and 191 cases it predicted no, where it was actually yes. Okay. So the confusion matrix, this is how it is used. Now accuracy, right? Accuracy is nothing but the sum of the diagonal divided by the total. That's all. So 3103 plus 1102 divided by the total cases. So how many cases did it accurately predict versus total number of cases? So you can get accuracy value for training, you can get accuracy value for validation. I also told you that these things predict probabilities, right? The leaf nodes are essentially combinations of data points, and the proportion of the training data points gives you the probability of the label. So 3 red and 2 blue means 3/5 probability of red, 2/5 probability of blue. And there is a method called predict proba. Okay, so once you fit the model, you use predict proba, you can get these probabilities. For X train, as you can see, these are very so probability should not look like this, right? 1 0 1 0 0 1 1 0 1 0. This is nothing but overfitting again. This just means that all my leaf nodes are pure, which is also why my tree is not even showing fully, right? When I tried to show my tree fully, it didn't show. It took a lot of time because the tree has actually made so many branches that all my leaf nodes are having one data point, which is why you're seeing these probabilities 1 0 0 1. Typically you should not be looking the probabilities like these. Okay. Anyway, so the next thing what we can do is we can predict, correct? We can use the predict method to get the predictions of the trees. Okay. So these probability values are based on the actual data points inside the leaf nodes. This prediction is what the leaf node has been labeled. Okay. So this is where we need to see, the error and everything. So training predictions, just predict using the training data. Validation predictions, you predict using the validation data. Okay, I have my predictions. Now you can see these predictions, of course. Well, preds, yes, yes, no, no, yes, yes, no, no. This is just churn, right? These are the churn predictions for the validation data, right? You can also check the train preds, right? These are the churn predictions for the training data. So here, if I just show X train, and maybe I should just show head. Yeah. So here I have customer ID 5339 PXDVH. The prediction according to the tree is no. This person should not churn. Okay. Similarly, this person should not churn. This person 3583 EK APL should churn. And of course, you can check, you can match it with the original data frame, and that is what we are going to do. Before that, there is another method called confusion matrix method from the same Sklearn matrix. Here you give the actual y values, that is whether they churned or not, and you give the predicted values. Okay, prediction values, where is it coming from? It is coming from model.predict. So here you are comparing. Let me run this. You can see here 31031102. Now if you go back, you'll get the same number here, 31031102. Okay, so this is essentially a NumPy array. This is a visualization. That's the only difference, correct? And same way you can check for the validation also. Give the true validation target value. So you separated the validation data set, and in that validation data set you have people who churned and did not churn, right? So those target values, the real values, churned, did not churn, those are here, yval. And valpreds, this comes from the model.predict method on the validation data, which you separated and kept. So here I have 853, 185, whatever. These are the same numbers here, 853, 185, 191, so on. Okay. That's about it. Now, finally, I would like to mention that I am using accuracy score as my performance metric. So again, remember that there are two things going on. Okay. When you train the model, the most important thing is what? Objective function, cost function, correct? If you remember linear regression, the cost function was sum of square errors, SSE. The performance metric in that case was RMSE, MAPE, whatever that you are using on the validation data. Same way, in the decision tree classifier, the objective function while training is Gini index. Performance metric you can choose. So I am choosing accuracy score, like how accurate is my model? That's the question, as the performance index. Right. So for that, you directly use this accuracy score method. I mean, it's very straightforward, right? 853 plus 180 divided by total. That's all for validation. Same way, 3103 plus 1102 divided by total. What proportion of cases did you correctly predict? Yes to yes, no to no. Okay. So you have the same method here, accuracy score. You give the actual y labels and then you give the predicted label. Same thing, actual label, predicted label. Okay. So I can get train accuracy, val accuracy. I'm putting it into a data frame here with the name tree model 1. So I told you that it is overfitting, right? The training accuracy is 99.5%. In fact, just to do this, right? If I just do 3103 plus 1102 divided by 3103 plus 102 plus 20 plus 0, 0.995267. 0.99526. Okay, so this is how accuracy is calculated. Notice that the training accuracy is nearly 100%, 99.5%. What about the validation? 73%. Clear case of overfitting, right? So this is what we have learned till now. Tree is very good. It fits really well, but it fits really, really well, right? It tends to overfit. At this stage, we may be tempted to check, okay, how is this model performing on the testing data. So I might actually get the testing predictions. How do you get the accuracy? You have to go back and you have to predict on X test. So you get the testing predictions by predicting on X test, and then you compare Y test and the predicted test Y values with accuracy score. You may be tempted, but you shouldn't do that, right? We will only do that at the end. Let's move on to part 3. So till now we have seen some of the hyperparameters of the tree. What are the default values? We split into X and Y, input output. So input features are used to build the tree. You check the performance, the final performance, not final, but any performance you can check using the training and the validation. Now, by the way, again, remember, no one said that the training algorithm ensures 100% training accuracy. Not the case. If you remember linear regression also, you had straight lines, correct? And those straight lines will always have some error. Same way, here also, there is no such condition that it has to be 100% accurate. Okay. But decision trees will almost always be 100% accurate if you do not restrict them. Okay. And validation accuracy, this is what we are using to actually judge the model. Is it generalizing well, or is it memorizing the training data? Right? That's the question we are trying to answer. Is it generalizing or memorizing? So this case is not encouraging, right? 99% here, 73% here is very bad, right? Okay. So now let's start restricting some hyperparameters and see what happens. Okay. So suppose I go for large tree depth. So again, same, everything is same method. So I will not go into all the details from now on till the end of the demo. Same methods, right? Decision tree classifier, fit the model, plot the model, plot the tree if you want, get the train and validation predictions, get the accuracy, put it in the data frame. Okay. Same things that we have done before. The only thing I'm doing here is max depth I'm setting to 8. Well, let's see what happens. So I did everything, right? I did fit on training data. I visualize the tree if you want to visualize. And then I use predict to get the training and validation predictions. I use the actual Y values and the predicted Y values to compare for accuracy score. And I get the accuracy score for training and validation, right? And I put it in the data frame. So now if you see this model, slightly better, correct? Slightly better. So the training accuracy has gone down. But again, this is the same magic that we spoke about in linear regression. Can you see the magic? The training accuracy went down, validation accuracy went up. Right? Long back I told you it is very intuitive, but slowly you will start to understand why it's working. And here, as you can see, because I am limiting the training, right? I am not allowing it to memorize. Therefore, it has to learn to generalize. Okay. So the training accuracy went down, but the validation accuracy went up. Not bad. Right? Not bad. Now let us look for maximum depth equal to 1. Just one split. Okay. Same method, one split. So let me run this again. Of course, you can see here tenure is on the top. And there's only one split. So you have two nodes here. This node clearly very high impurity. This node has a very low impurity. Okay. Now it's almost generalized is what I can say. Now the question is, so you can see here, right? 99% training accuracy, 73% validation accuracy. That is overfitting. Here I have 73%, 73%. It is generalized, but is it good enough? Are you happy with 73%? We don't know. What kind of accuracy you want depends on your business problem. But you can see that it's better, right? So here I will not say that it is good, but I will say that it is starting to become consistent. Okay. So all of this is on tree depth. Okay. So low tree depth, less overfitting. More tree depth, more overfitting. Let's also look at another hyperparameter, minimum sample for splitting. So if you remember, the default is 2. If you see, right, the default for this is 2, which means if I have a decision node with 2 data points, it will split. Okay. Now that is bad. If you are going to such a detail level, out of 4,000 data points, which you're using for training, you are going to leave nodes which are which have one element. That is leading to overfitting, obviously. So let's keep a very high value. Let's keep 1000. Okay, so minimum sample for splitting should be 1000, which means if a decision node has less than 1000 data points in the tree, don't split. Okay, so let's again do the same thing, fit it and check the accuracy and all that. Okay, much better. Can you see the result? Much better. 78.7% training, almost 80% training and validation, almost equal and almost 80. So now we are getting somewhere, right? Now it's starting to feel better. It can be said to be a decent model in two ways. It is consistent, that means it has generalized, and it is good, right? 4 out of 5 accuracy. Okay. Now what happens if you set a low value? This should be, answer should come immediately from the audience, right? If I set a low value for minimum sample split, it will lead to overfitting. It has to lead to overfitting. So here I have set 50 data points. In other words, if the number of data points in a group or in a node is less than 50, don't split. But if it is 50 or more, split, correct? So it's a very small value for 4000 data points. In fact, when you work with larger data sets, 50 is very tiny value. So it should lead to overfitting. So again, let us check it. It has led to some amount of overfitting. It is similar to tree model 2A. Okay, and I think 2A was the one with the maximum depth equal to 8. So there is still some overfitting. So here you have 83% on training, better, right, in training, but validation, again, if you compare to the training accuracy, it's not good. Okay, are we now understanding how I am using the validation performance as and the training performance to judge which is a good model and which is not a good model, right? We have done this for linear regression. I think we did this for linear regression with the MAP values and things like that. Here we are doing it for classification using the accuracies. Okay. Okay, great. Let's move to part 4. Okay, part 4, hyperparameter tuning. Right, we have done this before. Let's do it in much more depth. Right, here we have a lot more hyperparameters. So what is the general idea? General idea is fit the model for a certain hyperparameter value on the training data, check its performance on the validation data. Then again, change the hyperparameter value, fit another model for the different hyperparameter value on the training data, check the performance on the validation data. Do this for as many hyperparameter values and combinations that you want to do. Okay, so let us start with tree depth. So here I am using NumPy arrange to generate a value of tree depth. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, I think, right? So these are my possible tree depths. I will initiate a data frame to store the results, and the for loop will run on this NP arrange. So let me just print it once so that it's obvious, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? Start is 1, end is 11 minus 1. That's how NumPy works. And the step size is 1. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. These are my possible tree depths. And I will do a for loop on that. Okay. So each for loop, build a decision tree classifier for the current depth. Okay, so 1, 2, 3, 4. For each depth value, you build a model. And then you fit the model on the training data. Okay, obtain the predictions on the training and the validation data both, because you want to compare performance of training validation. From the predictions, you can now use the accuracy score method to compare predictions with the truth values for both training and validation, and I will keep adding it to my data frame. Okay, so that I can get a nice printed result. Yeah, so let me just run this. Okay, so it has completed all the different models, and I can just check this once if you want to see. So if I have max tree depth 1, 2, 3, 4, these are all the models. Okay, I have 10 models, and these are all the training accuracies, and these are all the validation accuracies. Okay, the easiest way is to just plot it using a line plot or something. Okay, so I'm using a line plot. X is the index and Y is the validation accuracy. What is the index in the performance DF? Index is nothing but maximum tree depth. So this one. 1 2 3 4 5 6 7 8 9 10. Okay, and what is the y value I am checking? The validation. So I want to see how the validation scores are varying. Right now, you can of course also do both training and validation. Correct. So here I am only checking validation, but you can also do training accuracy, right? And you can just print it. So now you will get both the training and the validation accuracy score. Okay. So the training is the blue one, by the way. Default color in Python for now. They may change it, but default in Seaborn is blue. So the training is the blue one, and the validation is the orange one. Technically, what you should be seeing is close values between orange and blue. So that's happening at 5, that's happening at 3. Which of these is best? 5 looks like the best. Now, sometimes you can also directly look at validation. Okay, because in the end, validation is kind of like a unseen data, correct? So more validation accuracy is better for me because the model has been looking at unseen data. Of course, I can check training and validation for generalization, but in the end, what is important to me is the performance on the validation. So sometimes you may see results with only the validation curve. Sometimes you will see results with training and validation both, right? You are free to check both. I'm looking only at validation because I know my tree is going to overfit, right? I just need to look at how good it's doing on the validation data. So 80% at maximum tree depth equal to 5. So that looks like a potential good value. 6 also looks like a potential good value. Maximum tree depth 6 looks like 79%. 2 and 3 also look like 79%. So 2, 3, 5, 6. These are decent values. Okay. Similarly, you can do a hyperparameter tuning for another hyperparameter, right? You can say minimum samples for splitting. We know this parameter. So notice that I have used fractions here instead of numbers. If you go back to min sample split, here I use absolute numbers. So 1000 data points as the threshold. And in the smaller one, I used 50 data points in the decision node, correct? You can also, instead of putting actual number of data points, you can also specify proportion of the training data. So 0.01 means 1% of the training data. Training data is 4200, so 1% means 42, right? So 42 will be the minimum sample split. And again, this is an NP A range. So the values it will be checking is 1% of 4200, 2%, 3%, 4%, 5%. So it is increasing the threshold for splitting. Okay. So that means what? This has to be the most overfit, like 1% means 42, minimum samples for splitting. It's a very low value. So, lot of splitting is going to happen. That should be the overfitting case, and 0.15, 15% of 4200 should be the generalized or the underfitting case. We don't know, we will see. That is exactly why we have this tuning. Okay. So again, same thing, you declare the values you want to look for, build a tree model with the specific value that you're looking for, and then just same thing, predictions, accuracy, performance. So don't worry about this. Okay, if you encounter things like this, that's just an internal Python computation thing. Sometimes it at 0.06 is read as 0.06005 or something. Basically it is 0.06. Okay, and this is 0.07 obviously. You can of course just round it if you don't like, right? Sorry. Yeah, so you can round it if you don't like, but I usually just leave it as it is. Okay, fine. Yeah. Great. So the training is complete for how many models? 1, 2, 3. There are 15 models. Okay. Again, plot the validation accuracy versus the index. So if you plot, in fact, you can plot the training one and also check it. Training. Okay. So the blue you are seeing is the training, and as I told you, the smaller min sample split is overfitting, which is why for a smaller min sample split you have very high training accuracy, blue color, correct? And it's going down, right? So you are controlling the overfitting by increasing the size of the decision node where it should stop splitting. And what you're looking for is a decent performance and general matching with the training. So I can see 0.09 is nice, 0.1 is nice. So these are all nice values, right? So 9%, 10%. And what is 10% of 4,200? 420. So around 400 to 500, min sample split looks like decent. Okay. This is also decent, 0.04, but slightly suspect because there is some overfitting happening here. Okay. So the training is 81, 82%, and the validation is around 79%. There's a very, very, very minimum overfitting happening here. These are much better and safer values. Okay. So yeah, you can go for this if you're willing to take the risk with the tiny bit of overfitting, or you can go for this for safer values, right? So this is the advantage. Sometimes you don't just look at validation, you look at training versus validation, right? For comparing the performance. So what, and I put a question mark here. And why have I put a question mark here? Because have we really rigorously checked all the hyperparameters and the combinations? Because here, in fact, if you go back, you are checking minimum sample split, but did anyone wonder what is the max depth? Max depth is none. So I am using full maximum depth, right? But I'm putting condition on the minimum sample split. Is this the right way to do hyperparameter tuning? Answer is no. This is not the right way to do hyperparameter tuning. The reason we are doing this is to motivate that you can, of course, analyze the performance of a model based on one hyperparameter value, right? And since linear logistic, mostly they have only one hyperparameter, so there was no need to worry about combinations of hyperparameters. But now in decision trees, there is a need to worry about combinations of hyperparameters. So I wanted to show that you can still do the analysis with one hyperparameter change, but at the cost of keeping all the hyperparameter constant if you're using for loops. This is where in the next session, we will discuss certain more advanced methods to do the tuning for combinations of hyperparameters. Okay, we'll do that with random forest. For now, what we'll do, we will just use an optimal tree depth value from before. So in here, maximum tree depth equal to 5 looks like the safest. In fact, to check the actual thing, you should check with training as well. And this is looking very bad because I have to retrain my model. Yeah. So 5 looks like the safest, right? After this, there is a lot of overfitting. You can see the difference between the train and the predicted. There's a lot of overfitting. So 5 is very sweet spot for the tree depth. Okay, it's very well generalized and it is having decent accuracy, 79, 80% something. So let me just fix the tree depth value at 5. Then I will tune for minimum sample split. Okay, so here if you see inside my code, I have kept max depth as 5. Then with max depth as 5, check the performance for the various other hyperparameter. Okay, so again, let's run this loop and check what's happening here. Now you see a very different thing going on, right? So in fact, if you want to check this properly, very interesting, very, very interesting. So this is weird. This is very weird, right? So obviously these blue points are overfit, correct? For these minimum sample split, this is overfit, right? But the validation is also performing well. This happened because you kept maximum depth equal to 5. When maximum depth was equal to none, this was not the case. Okay, so this is actually looking like a good sweet spot for the 2 hyperparameters. These are also good. Like if you go down the curve, 0.13, 0.14, these are also pretty good actually, right? So here you have around 78.5, 79. So it is generalizing well here. It has generalized luckily here. Now the question is, which one is going to do better on the testing data set? And the answer is we really don't know. Okay, we don't know if this thing is going to perform better. We don't know if this thing is going to perform better. That is one problem. Another problem is, how many things can I keep checking like this? You tell me. If you actually want to check everything, it has to be for loop inside for loop inside for loop inside for loop inside for loop. How many ever hyperparameter combinations you want to check? That's an inefficient method, right? That's inefficient computation. So that's another problem, right? So we'll address these supervised learning general problems in a section in the next session when we deal with random forests. Okay. So for now, I might choose 0.04 and maximum depth equal to 5. So we can do that. For example, here I have taken minimum sample split as 0.04, maximum depth equal to 5. I am taking a risk. Okay, I am taking a risk here to see, okay, is this going to generalize well on my testing data set? Anyway, so once you find an optimal combination, you don't need the validation set anymore. Correct? Why do we need it? Once you found out, okay, this combination is looking nice, you just use the validation with the training. That's all. So you concatenate the train and the val so that you provide more data to the model. Okay, more data is generally a good thing. So you can concatenate the validation and the training. So now you have almost 5,000 something data points, right? So now you have the new X train and the new Y train values. Finally, use what you think is a potentially optimal combination for the hyperparameters and you fit it. Okay. Once you fit it, of course, you can go ahead and visualize it if you want. You can check feature importance if you want, all that you can check. The main thing we are interested is the final training and testing accuracy, right? So now the model has been fit on X train new, Y train new. So here you get predictions on X train new and the remaining X test, which till now has not been used. Okay, this X test has not been used, and then you obviously you get the accuracy values.
In today's rapidly evolving business landscape, machine learning and AI are no longer buzzwords. They are essential tools for staying competitive. Are you ready to lead the AI revolution in your industry? Upgrade, in collaboration with IIIT Bangalore, brings you the Executive Diploma in Machine Learning and AI. This program is designed for ambitious professionals like you, seeking to leverage AI for strategic decision-making and innovation. Gain hands-on experience with cutting-edge technologies, learn from renowned faculty, and network with industry peers. Elevate your career, drive business transformation, and position yourself as an expert in AI. Enroll today and future-proof your career.
So the agenda for today's session, we'll start off with ensemble methods. And as I said, these are not models as such. These are actually techniques or methods which are used on top of machine learning models. Okay. So there are a few kinds of ensemble techniques. We'll understand those, right? And then we'll pick one of those ensemble techniques and we'll apply it to decision trees. Okay. So that gives us random forests, which you can say now it's a machine learning model because the ensemble technique has been applied on the decision tree model. So together it forms a new model called the random forest model, right? We'll study that. And we'll also study, as I said last time, for loops are not necessarily the fastest or most efficient or the most meaningful way to do hyperparameter tuning and model evaluation and those kinds of things, yeah, right? Which is finally the primary thing to do in supervised learning, right? It's kind of the crux of supervised learning, right? How do you do your model evaluation, right? So so there's a very formal technique which is used quite popularly with most of these supervised models, which is called cross validation. Okay, and it has a very standard implementation in Python, which we will see. Okay, and finally we'll do a Python demo which demonstrates both random forests and the cross validation method. Okay, and I do have a few other things that I'll probably talk about in the Python demo. All right, great. So let's start with ensemble methods. Okay, the data set is the same that we'll use to understand the concept. It's the same as last time. So essentially, we have the different customers on the rows, that is the observations, and we have various features such as gender, job, income, age, amount, and churn. And one of these features is churn, which we will use as our target variable. And just to recall, yes, churn means that the person stopped subscribing to my service. So in this case, the person stopped coming to my coffee shop, right? If for a yes churn. No churn means they are continuing. Okay, so that's a very classic business problem, right? We'll quickly revise decision trees before we go into ensembles. Now, what were decision trees? Decision trees were essentially sets of sequential linear conditions that we put on input features of a data set, right? And these linear conditions, they divide the data space into chunks, right? Into small subregions. And then each subregion you assign a class label or a numerical value based on what task you're doing. Okay, if you're doing classification, you're assigning a class label. Yes churn, no churn. If you're doing a regression, then you'll be assigning different output numbers, right? Prediction numbers to the different chunks. So that's essentially what decision trees are doing. Then what happens when a new data point comes and you want to, predict, what's happening with that new data point. So whichever region that new data point falls in, you give the same label or the same output value as that region. Okay, so prediction is done. Great. How do you determine which region it falls in? It's just a simple matter of coordinate geometry, correct? You just go through the conditions and see which conditions are being satisfied. So you'll be able to go through the tree and find out, okay, this is where my point is lying. Great. Now, how did we build the tree and optimize it? How do we know it works? Why should it work, right? So we use something called the Gini index or any equivalent impurity measure. The idea being that as you build the tree, the purity of the groups or the subregions that are forming should be higher. Then my predictability will be better. Okay. So some of the trees that we saw in the last session, this is the the main tree for the 10 customer coffee shop customers, right? So amount less than equal to 2032, and then again amount, and then again amount. So this is a single feature tree, obviously. And we also saw like multiple feature trees, right? We saw, okay, there was a question on app subscription with fees and amount of time spent on the app per day. So your first feature is on the top, and then the next feature hours is the next level, and then again you get another feature, same feature, maybe different feature, right? So we understood all this last time, and we also understood that we don't necessarily allow the tree to fully form, right? It's almost always better to prune the tree. And at the end, when we were doing the hyperparameter tuning, we saw exactly what pruning looks like, and we saw, okay, there's a lot of overfitting going on if you do not prune the tree, and if you don't let the tree grow, then there's a lot of underfitting going on. It's a very, very, very sensitive algorithm, correct? Nature or design of the algorithm, very simple, right? But the model itself is very sensitive to the hyperparameters and the data. And finally, we kind of saw the advantages and disadvantages. And advantages, we saw a lot of advantages, right? We saw that, okay, the tree is really easy to understand, interpret. So you can see, just by looking at the tree, you can see, okay, this person is older than 50 years. Therefore, they may not, continue with my coffee shop, something like that, right? It's very easy to interpret the tree. There was almost no data pre-processing, right? If you remember the demonstration, Python demo, I don't think we did any major pre-processing of any kind, right? Scaling, this, that, outlier, nothing. We did none of that. So that's a big advantage. It's robust against outlier, right? And it can also handle nonlinear relationships well. And we also saw that it can be used for just specific data analysis, right? Just core data analysis also you can do with this ML model called decision tree. By way of feature importance, right? It generates these feature importances based on how frequently a feature is called, how important it is in the tree, right? Takes all those factors into consideration, and you get numerical importance values. So then you can sort it out and see which is your most important feature, whatever, correct? So a lot of advantages. And then we also saw disadvantages, right? When we did the Python demo, it was very obvious. I think when we were doing the hyperparameter tuning, right, it was going very slowly, right? And in fact, when we tried to show the tree for all the max depth, which I don't know what the max depth was, right? Because we didn't show it, because the tree was taking time to even show, right? So it is a very, very resource hungry and time consuming algorithm. Okay, that's clearly a disadvantage. It is sensitive to data changes, which leads to completely new trees. Now, this is somewhat disadvantage. I won't say it's the biggest disadvantage, right? Your features may shuffle up and down, your nodes may change a little bit, but that doesn't mean that in the end your tree is like completely different in terms of functioning, right? In terms of functioning, it's more or less the same, but you do lose ability to track. You do lose ability to make claims, right? Therefore, it's a disadvantage. And obviously, it's prone to overfitting. Now, this is where some certain things come in, right? And if you remember, there was this max features hyperparameter. We spoke about it, very shortly in the hyperparameter tuning section of the last session. We spoke about it, but we didn't implement it. And I remember telling you guys that, look, it sounds nice with decision trees, but it goes really well with something called random forests. So today with random forests, we will, have to use this max features, and I'll explain to you soon why. Okay. So the point is that we can actually try to deal with a couple of these disadvantages at the cost of resource. So basically, can we try to handle this sensitivity issue to data? Can we try to handle this overfitting issue and underfitting issue, by the way? Because if you don't let the tree grow, it does underfit very badly, right? So can we handle these things at the cost of resource? That's the question. And typically the answer is yes. Okay. And it comes down to a class of techniques called ensemble techniques. And there are different paradigms, different ways of thinking in ensemble techniques. Okay. So the motivation behind this is what? If each single model, right? Oh, by the way, what's ensemble? Ensemble just means group, or you can say team, right? I think the simplest word I can use in place of the word ensemble is team. So basically, if a single model is sensitive to data changes, then maybe a team is, can average out those inconsistencies, right? And maybe if a single model has a very high chance of overfitting or underfitting or those kinds of issues, then what if a team of models, can they alleviate the issue? And this is the primary way of thinking in ensembles. Okay. And these ensemble techniques, this team of model techniques, right? It can be applied to any machine learning model, but it has been very successfully employed with decision trees. Okay, it's typically used in conjunction with decision trees, and some of the most popular machine learning models out there, some of the models which even make it to top Kaggle competitions and things like that, right, have been ensemble techniques applied on decision trees, right? Quite interesting to see that. So the major kinds of ensemble methods that are typically used in the industry and studied in academia are these three. Okay, one is called boosting, one is called bootstrap aggregating, and sometimes it is shortened to bagging, and another one is called stacking. Okay, so what we'll do is we'll first look at boosting and stacking in a little generic way. Okay, then we'll go into bagging in detail, right? And we'll apply the bagging method on decision trees, which then produces what we call a random forest. Okay, that's kind of going to be the flow. So I want to get boosting and stacking out of the way just to give some motivation of how this works. So please look at the screen. Now what you're looking at here, and before you see all the data on the top, forget about the data, look at the second row. Okay, look at this. So there's one model here called base model. Okay, then there's another model called error model 1. There's another called error model 2, and so on, right, till error model n. So basically now I have a team of models. Okay, so this is boosting technique, how boosting works. Okay, so I have a team of models. Now what does the base model do? The base model works on the original data. Okay, and of course it's doing nothing. It's a model, it's a machine learning model, it fits on the original data, it makes some prediction. That's all it does, right? It's a machine learning model, make some predictions. Now I could end the story there, right? I can close the story there and say, this is my machine learning model, this is my prediction error, end of story. But boosting is a technique wherein you use another machine learning model, right? It could be the same kind of model or a different kind of model. Typically they are the same, right? So if the base model is a decision tree, then you will use another decision tree, error model 1. That's another decision tree which predicts the prediction errors and not the actual target values. So whatever prediction error you got from the base model for your data, suppose, right, for your training data, suppose we have 10 data points. Therefore, you have 10 target values, 10 churn values, right? So your model made some predictions on those 10 data points. Your model is not 100% accurate. So whatever prediction errors are there for each of those 10 observations, use that as the new target variable. Okay, so error model 1 is now a decision tree which works on the same input data but predicts the prediction error from the previous model. So now its target is the error. Okay, similarly, now this second model, the error model 1, is going to have more prediction error. Now you use another model to predict the new prediction errors, right? And now you can actually go on and on and on and on. Okay, each of these green boxes in technical language, it is called estimator. Okay, so when we do the demo, you will see parameter name estimator, right? Each of these green things is called an estimator, right? Each ML model here is called an estimator. So what happens after all this? Now you have a team of models which is able to predict the prediction error to n number of steps. All you need to do is backtrack. That's all. You backtrack from those errors, right? You remove those errors little by little by little using all these models through something called an aggregation function. Okay, so you take the information of all these prediction errors, right, apply it to the original prediction that you have, aggregate it, and then you get a final prediction. All right, so this is boosting. Now of course there are many ways in which boosting is implemented, right? So I've shown you very sort of basic understanding of boosting, very sort of basic way in which it's implemented. There are, you know, variations of this implementation, but the general thought process is the same. General thought process is the same, right? One model makes the predictions, the second model predicts the prediction errors, and then the third model predicts these prediction errors, and later you aggregate all this, and as much error you can remove, that much you know, your accuracy and your prediction performance increases, right? Now before I continue with stacking and other bagging and those things, right, what I want to say is that if your base model is already a overfit model, then this doesn't make any sense, correct? If your base model is getting 99% accuracy, things like that, this doesn't make sense. So typically when you do boosting, bagging, stacking, these kinds of ensemble methods, each estimator, generally we restrict them a lot. Okay, each estimator is restricted a lot. So in a sense, what happens is they become very weak models. So your base model is not a good model. Your error model 1 is not a good model. Error model 2 is not a good model. But the team is a good model. Okay, so it's actually a balance between how weak your estimators are and how strongly you apply the ensemble technique. Okay, and in very simple terms, if I translate that, how many estimators are you using, what is the learning rate you're using. Those are the things which apply to boosting. And I would say once after this session, you can actually explore boosting on your own, right? Okay, stacking. What is stacking? It's a very similar concept. Okay, very similar concept. In fact, this is a even simpler, right? So what you do, again, as you can see, I have a team of models. Okay, model 1, 2, 3, 4, 5, model n. I have a team of models. Now, in this case, what happens is each model fits on the same data. Okay, each model, so decision tree 1, decision tree 2, decision 3, 4, 5, 6, all of them are being fit on the same data. Okay, and then there is an algorithm that we will define separately. So there's this thing called combiner algorithm. Typically, it could be a linear combination. Typically, okay, typically combiner algorithm could be a linear expression of the outputs. So model 1 output, model 2 output, model 3 output, model 4 output, model n output. You take all these outputs and you put those outputs as an input to a linear model. Then you train that linear model. Okay, then you train the coefficients of the linear model. So again, you see, if my team is weak, right, if each of my ML models is weak, right, then the combiner algorithm can increase in strength to compensate for the weakness. Now, I've mentioned boosting, I've mentioned stacking also. You might be thinking, why should I go with weak model? But by this time, I think, guys, we should understand why we're trying to go for weak model. Try to remember the last session, right? If I went for maximum depth, right, what happened? 100% training accuracy, right? 99.7% training accuracy. What happened to my validation accuracy, right? 70, 60, right? And that was a data set with 7,000 data points. What if you had 20,000? It will be 100% training accuracy. You will get very, very bad validation and testing accuracy. The reason we want weak models, right, is overfitting, essentially. Okay, essentially overfitting is a problem that plagues decision trees for sure. Okay, so the idea is you make the tree, each tree you make it weak, and then combine them into a team and train the team to be strong. Okay, so as I said, I'll not go too deep into boosting and stacking. We'll understand bagging in a little more detail. I would urge everyone to read about stacking and boosting later. In fact, boosting, I would say definitely read, because you know, some of the most popular algorithms on decision trees come from bagging and boosting. Okay, now let's talk about boosting, and this is a very interesting method. Okay, so here is my original data on the left. What I'm going to do is I'm going to replicate this data set by taking random subsets. Okay, so I have a random subset of my training data here. Let's say random subset 1, and then I have random subset 2, and then I have random subset n. Now, what do these random subsets look like? We will go into that, soon. But essentially, what you're doing is you're picking observations from the original data. So suppose my original data had 10,000 data points. Okay, each of my subset can be 1,000 data points. That's all. Now you tell me what's going to happen if I build a tree on 10,000 data set, and if I build a tree on 1,000 rows, right, 1,000 observations. Which one is going to overfit? Of course, the one with 10,000. It has way more information, and we know that the tree tends to overfit. So what you do in bootstrap aggregating or bagging is you create these bootstrapped samples. This process is called bootstrapping. When you take these random subsets from the original data, it's called bootstrapping. Okay, so you create very, very small samples. You have 10,000 original data, you create 1,000. You create these many subsets with randomly picked observations. Okay, and I'm not even replacing, like you can pick the same observation 2 times also. Okay, that's how it is. So random subset 1, just randomly pick whatever comes from the original data. Okay, so there's a chance that one row may be picked twice, but generally it doesn't matter because you're going to have so many subsets. Okay, for each subset, now you build a model. For each subset, now you fit a decision tree. And even in this decision tree, now I am showing you random subsets, right? I'm showing you 1,000 random data points, right, from the original data. So already my tree has less information to work with. On top of that, we will penalize the tree even more. So here, max features. You remember we spoke about this thing called max features. Max features. So here we will implement the max features hyperparameter. So if my original data has 6 features, I will only use 2 or 3 randomly to build the tree. We spoke about max features in very short, very shortly last time. What essentially happens is, if you have 6 features and you say max features equal to 3, then each level of the tree you will randomly pick 3 features and only search the splitting for those 3 features. Okay, so there are 2 restrictions already for each tree. Here there are 2 restrictions. First restriction, I'm not even giving the full data. Okay, second restriction, I'm not even giving the full features to search from. So now you tell me that each tree is going to be weak or strong. Each of these trees is going to be weak. Okay, each of these models is going to be weak. Each of these estimators is going to be weak. But what typically we see in ensemble methods, and this is why this is popularly used, is that the team of the weak estimators tend to do better than the best tree. That's the funny part, right? So maybe it is 1% better, maybe it is 10% better, whatever. But generally, they tend to perform better than the best single tree. So what I'm saying here is, using these ensemble methods, a team of decision trees does better than a single overfit tree or a single, optimum tree. Call it what you want. And how do we get the final output then in the bagging method? Essentially, you just do a majority. So now you have n trees, right? Weak trees, of course. What you do is you take the predictions from each of these trees. If it is classification, then you just take the majority output label, right? If it is regression, you take the average of the predictions. Okay, so essentially you are having multiple predictions. This is why it's called an ensemble technique. Okay, not exactly a model. Okay, ensemble is not a model, right? It has so many steps. First step is to create the bootstrap sample. Second step, you fit the tree. Third step, you get the predictions from each tree, and then combine it using some function like an majority or an average. So it's actually a bunch of steps. Okay, which is why it's called ensemble technique, not model. Although if you Google, people will say ensemble model. Technically, these are called ensemble methods or techniques, not models. Okay, so then you get your final prediction. All right, we'll see this in more detail soon, but this is typically how bagging works. Now, if you use decision trees as the base learners, in other words, estimators, right? I told you the word estimators. If you use boosting on trees, then you will get something called gradient boosted trees or GBTs. Okay, these are also very popular models. If you use the bagging technique on decision trees, what you get is random forest or RF. These are also extremely popular ensemble models. Now I can say, after applying on decision tree, now it becomes a model, right? So yeah, so these are the 2 most common, popular, and successful in the industry, right? Some of the top Kaggle competitions and everything, you will see GBT, RF, things like that. Okay, so I would urge all learners, right, everyone, to go through GBTs as additional reading. Once you understand random forest, and I've already given you the basics of boosting, right? And once you understand random forest, doing GBTs on your own wouldn't be that hard. Okay, so once you are comfortable with all of this decision tree, bagging, random forest, boosting concept, after all that, go and explore GBTs. Okay, yeah, so in this session we will quickly focus on random forest. Okay, random forests. Now a quick intuition exercise, and then we'll get into it. Okay, so let's go bullet point by bullet point. So suppose that the probability of a single tree being correct in its output is 70%. Basically, I'm saying it has 70% accuracy. Okay, so suppose there is a single tree whose performance is 70%, means 100 out of 100 times it is 70 times correct. That means 30 times you are wrong, correct? This means that if you rely on only one tree, then you have 30% chance of being wrong in your prediction, correct? So this is what the second bullet point means. So if you use 100 trees, what you're saying is that we can expect, and I would like everyone to focus on this word, expect, about 70 of these trees to give us the correct prediction, and 30 trees will give incorrect prediction. And why are we focusing on the word expect? I hope everyone can remember back to probability distributions, expected values, and things like that. We know that there is this thing called law of large numbers, right? As you have more and more and more samples, what happens is that the mean, actually the real mean, matches with the theoretical expectation. So if I say that my single tree is 70% accurate, but I only try it out 2 times, then I will not be able to look at the number 70 at all. No chance. Either it's going to be 50-50 or 0-100 or 100-0 if I only implement it 2 times, right? We have to implement it n number of times. Then the expectation, whatever expectation you have, will match with the mean output. Okay. So I've used the word 100 here, the number 100. Think in terms of 10,000s. Okay. So if you use 100 trees, what happens? You can expect 70 of these trees to be correct and 30 of them to be wrong. Why? Because each tree has a 70% accuracy. Okay. Now just think quickly, right? If we use a majority vote on these 100 trees, what's going to happen? Then we'll obtain correct predictions almost 100% of the time. No doubt. So there's no question of going wrong in the training, in fact. And you will learn soon when we do the Python demo. Random forest also overfit if you don't control the hyperparameters. These things also will overfit. Again, think, okay, if your single tree, you made it really weak. Okay, now you saw in the previous session, even the simplest tree was giving like, the training accuracy was 99%. Right? We had to restrict till, I don't know, 72-75%, something like that. I'm saying restrict even more. Suppose you restrict the tree even more, make it 60% accurate, make it 70% accurate. One tree. Now, you have many such trees, 100 such trees, okay, each having 70% accuracy. Okay. If you use a majority vote on the output of the team, right? If you use a majority vote on all the 100 trees, then my prediction of the team is going to be 100% correct all the time, almost. Why? Because I can expect at least 70 of those trees in any iteration, in any situation, to be correct. Because one tree has a probability of being 70% correct. Okay. As I said, if you take this tree and only do it 2-3 times, then no. Then you are not using the law of large numbers. But if you take the same weak tree and do it 1000 times, definitely 700 of those trees will be correct. Now, after 700 trees are correct, just take the majority, right? 700 are correct, 300 are wrong. What's the majority? 700. Then what's going to be the output? Whatever the 700 told. And we know that's correct, right? We know that 70% is the accuracy rate. We know those are the correct answers. So almost 100% of the time, if you take the output of the team of these 100 trees, your predictions will be correct. So this essentially says that however weak you make your tree, and if you see the bullet point here, theoretically I'm saying, okay, don't hold me accountable for this ambitious statement, but in theory, if your tree is even 51% of being correct chance, then a team of 51% correct trees will be 100% correct if you take the majority vote. Why? 51-49. Almost always you will get slightly more correct answers and slightly less wrong answers. So when you take the majority, it will be correct. So notice how weird, using the the rules of probability, laws of probability, they're being used, right? It's being used to make sure that a team of weak estimators are always correct. Therefore, you have solved your training problem. Okay. Now you can make your estimators as weak as you want. Okay. And then you can use an ensemble method like bagging, and your training is going to go fine. no problem. Okay, the other problem is the overfitting. We'll come to that later. But yeah, so this is essentially the intuition behind bagging. Okay, why use so many weak estimators and how they solve the training problem even if they are weak estimators. Okay, so it's a very, I would say, unconventional way of thinking. As I just said, it's so weird, right? Using loss of probability, making all the models weak, putting it into a team, but it works. Right, this stuff works. And that's why these models, as I said, right, they're some of the most popular winning models on a lot of competitions. And in fact, a lot of companies use these very heavily, right? Random forests are used almost everywhere. So this is the intuition. With that intuition, let's get into an introduction to random forests. A random forest is essentially a group of decision trees. Okay, each tree is trained on a random subset. I've already told this. The random subset is actually selected each time. Okay, this is done with replacement. These two things constitute the term bootstrapping. Randomly pull out observations from the original data to fill your sample. Do it with replacement. That means sometimes you can get duplicate observations in your sample. No problem. That is restriction number one, right? This randomness is restriction number one. Another randomness is this one. Each decision split in each of these trees, again you use a random subset of the features. So what you're doing is you're randomly chunking the observations and you're randomly chunking the features everywhere. It's like a matrix of randomness, actually, right? Each tree will be very weak. If you pull out one tree, it's going to be very weak. Okay, so random subset is your training data for the weak estimator, and on top of that, random subset of features in each split. And how do you control this? There's a hyperparameter called max features. Okay, so after that, what do? You record the output of each tree. In case of classification, you take a majority vote. In case of regression, you take a mean. Simple. How does it work? Let's see for classification. And this is what I step by step I told you. We'll go through that, right? So the first step is the preparation of the bootstrap samples. On the left, you have the original data set. This is the 10 data points, Aarti, Darshan, Isha, right? These are the 10 coffee customer data points. What you do, suppose my bootstrap sample size is 5. Okay, so you see the first sample here. What it has done is it has picked Aarti, Darshan, Gayatri, Lokesh, Zishan. 5 random observations have been picked. My bootstrap sample is ready. Again, do the same random picking, right? Bootstrap sample number 2. Now if you see sample number 2, it has Aarti, Isha, Monisha, Zishan. Isha 2 times. Okay, do this again and again, how many ever times you want. Now how many ever times you want means what? It's the number of estimators, and that's what I've written here, right? The number of observations per subset and the number of subsets, both. These can be manually specified. And what is the meaning of manually specified? Hyperparameters, that's all. So number of observations per subset means what? It's the size of the bootstrap sample. How small or how big do you want each tree to train on, right? So what's the size of your bootstrap sample? That is also a hyperparameter. And the number of subsets, right? How many estimators are you actually using? What is the size of your team, right? That is also a hyperparameter. So I think by now it's become very clear. There's a lot of hyperparameter stuff going on here, right? The logic is simple. The base model is a decision, that is simple, but so many hyperparameters, right? Number of observations per subset, that is the size of the bootstrap sample, number of estimators, and then you have max features, right? At the same time, you have to control the maximum tree depth also, right? So you have to put n number of restrictions. Okay, some of these hyperparameters are decision tree hyperparameters. The max depth is a decision tree hyperparameter, and some of these hyperparameters are the ensemble hyperparameter. So for example, the size of the subset, that is a hyperparameter for the ensemble part. Together, all these hyperparameters are associated with what we call the random forest model. Okay, anyway, so that's how you prepare your bootstrap samples. Now you train the individual learners. By the way, these are also called learners. Estimator, model, learner, right? All mean the same thing. Now you train them. So you have your bootstrap samples, and at each decision tree node, I told you that we will be not using all the features. We'll use a subset of the features. right? Random subset, that too. And then the decision split will only search those features and then split. Okay. So you build your trees and then you fit these decision trees on the subsets, on the bootstrap samples. So now you have, n number of decision trees which are ready to predict. That brings me to output. So now I have n number of decision trees which have been fit, which are ready to predict. You just make the prediction and you do an aggregation. I said for classification, you do a majority vote. For regression, you do a mean. That's how you get your final prediction from this random forest model. Okay. Just a quick example of classification. So, this is what your tree might look like. It's a weak tree. It goes only to level 2. Okay. I can see 2 blue nodes. I can see 1 red node. This is how a typical weak tree is going to look like. So suppose the prediction from this tree is blue, and suppose this one also is blue. Suppose there are others with red, blue, whatever. And you take a majority vote on that, and the answer is blue because I got more blue predictions than red predictions. Okay, which could be yes churn or no churn or something. In case of regression, this is what a typical regression tree looks like. For those who did not get the chance to explore a little bit about regression trees, this is what regression trees would look like. Your leaf nodes will be associated with constant values, basically. Okay, there might be 10 data points inside the leaf node, but each leaf node will be associated with a constant. Okay, constant output numeric value. So this is how regression tree looks like, right? So suppose the first tree output is 24, suppose the second tree output is 22, so on and so forth. Okay, and you have 100 such estimators. Just take the mean, right? Take all the outputs and then you take the mean. This is how you get for regression. So I want to speak about a few things now related to random forest. So by the way, that's all it is. Okay, if everyone is kind of expecting that, okay, where is the random forest technique that I'm supposed to study today, we are done. I'm being very honest here, right? We are done with understanding how random forests work. We are done with how bagging works. Okay, that's all it is. I've given you the steps. That's all it is. See, lot of these machine learning models, right? Your scientists and statisticians, mathematicians, ML scientists, they kept thinking, and even now we keep thinking how to make things simpler. Okay, so many people would sort of think of random forests and these kinds of things as complicated or anything. Not at all. Their implementation is complicated. The resource complexity is complicated, right? But the thinking behind it is quite simple. That's all it is. I think we can summarize it right now, right? You have a data, okay? Make small random samples from the data, fit very, 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 very weak decision trees on all of these samples, take an aggregation output, random forest. That's all. Done. Okay. So now I want to speak about a few things related to random forest. There are, as I said, there are so many things going on. So it's important to keep everything close to hand, right? There are so many things going on in the model itself. Right? So first, a note on randomness. So immediately, I think I would draw your attention to this picture. Most of us would have seen such a metaphor before. It's this elephant in the dark room or something, right? There's a metaphor in which, there's an elephant in the dark room and there are 5-6 people all touching the elephant. The guy touching the trunk is saying it's a snake. The guy touching the tail is saying it's a snake. The guy climbing up the ladder is saying it's a building, whatever. This is a metaphor for how, random forests work. My point is, after all of these people, touch the elephant, and then they go to a room, sit down and talk, sooner or later, they'll come to think, was it an elephant? Now that person may be not very confident in the answer. Okay, maybe 70%, confidence in the answer. But many of them will be having the same 70% confidence that's an elephant. Then if I allow that group to make a majority call, then the answer is elephant. Okay. So this itself should tell you something about the hyperparameter, right? If the number of estimator is less, it will underfit 100%. If the number of estimators is high, it will overfit. Right? Anyway, so where is this randomness coming from in the random forest? We already know. One is bootstrapping, right? You are randomly chunking the original data into random bits with repetitions and all that, right? So in itself, each subset is meaningless, to be very honest. If your original data is 10,000, right, each bit is 1,000, and that too with multiple duplicate samples. It's not even a meaningful sample. Therefore, the tree you build on it is going to be very weak. And again, feature subsets. Each time you do a split in any of these trees in the random forest, you're restricting the feature subset. Okay, so your original data may have 20 features. You are using 4 features, 5 features randomly. So the root node for one tree will take random 5 features and search. The next tree root node, another random 5. Right? And after splitting, level 1, again random 5 features to search for the split. So these two are the main sources for randomness, which lead to what we say somewhat weak estimators or weak learners. But together, if there are sufficient learners, they will perform well in a group. And this is essentially why this model has these techniques have gained a lot of popularity over the years. Okay, so there's another small thing that I want to mention called out of bag error. Now that we know how supervised learning works, right? So let's have a look at this. So there's this thing called out of bag error. Okay, now here bag means bag, I think, or at least let's think of it as bag. It's also called OOBE. Okay, so if you're gonna Google it later or something, OOBE, out of bag error. Basically, the random forest, if you see, each tree is using a bootstrap sample. This means that not every tree uses every data point for training, correct? So decision tree 1 does not use the full data set. Decision tree 2 does not use the full data set, which means that there are going to be some common data points which a group of your weak learners did not see. With that group, I can make a smaller random forest. And then I can test my prediction using that specific data point which the group of decision trees did not see. Okay, I'll explain in more detail. This is a good thing actually, right? We can use this unused data point. I say unused in quotation marks. I should say in quotation marks, because there will be some tree later which is using the data point. But there will be many trees which did not use the specific data point from your original data. So you can use this as your validation data. While training the random forest, you can also do the validation. So this is used as a self-validation technique sometimes. Okay, when you do random forest, this performance error is called the out of bag error. Right? So to give more clarity, suppose all of these data points are my total data set. Okay, I'm just showing 2 axes. Of course, there can be n number of axes. Each axis is a feature. Okay, so this is feature 1, this is feature 2. I'm just showing 2 axes. Now, if you see all the blue and green data points on the screen, these are my full training data. Okay, this is my complete training data is on the screen. Okay, now suppose I build a random forest with 10 trees. Suppose I build a random forest with 10 trees on this data. Okay, suppose I build a random forest with 10 trees on this data. Then suppose that there are 6 data points and I've put those data points in green color. These 6 data points in common have not been used by 4 of these decision trees. Which 4? You can see the 4. So I put red circles, for these bootstrap samples. Okay, so these 4 decision trees out of the 10 decision trees in my forest have used these bootstrap samples, which you can see on the screen. And these 4 decision trees did not use, in common, they did not use those 6 green points. Now I can make a small random forest from these 4 decision trees and test its output prediction performance on these 6 unused data points for this specific small random forest. Okay, and you do this for every data point by data point, you do this. So now this is for specific 4 trees. Then again you take combination of some other 4 5 trees or 6 trees, 7 trees. As long as you have at least one common unused data point, you can test how your random forest is performing as a smaller version of itself. So generally, typically, these do give you some indicative indication of how your random forest is doing. Okay, because in a sense it is validation. What you're doing is validation. So just to summarize this, out of bag error, you can think of it as a pseudocode. You think of it as a pseudocode, right? For loop. So for each data point in the data set, consider all the trees that did not use that specific data point. Okay, so maybe there are 5 trees, 6 trees, 7 trees, whatever, out of 100 trees, right? Consider all the trees which did not use that data point. Then consider, in a sense, a smaller random forest of these trees and use the random forest prediction method to predict for this specific data point, okay, which these trees did not use for training. Then you calculate the prediction error on this data point, right? And you store that error. You do this in a for loop for all your data points and then calculate the mean prediction error. This will give you a self-validation error metric. Okay, so while doing the training itself, you can get the OOB value. In fact, there's a parameter in the Scikit-learn method which says OOB. Default is false. In our demo today, we'll keep it false. I will leave this again for you all to go and explore. Okay, so default value of that parameter is false. You can set it to true, basically, right? And you'll get this OOB value. Okay. Now let's talk about some hyperparameters. Okay. Now a lot of the hyperparameters in random forests are exactly the same as decision trees because trees are the base estimators or the base learners for random forests, right? So many of these are going to be common, like criterion for split, minimum sample split, maximum tree depth, cost complexity, max samples leaf. All of these are common hyperparameters, okay, which will apply to every decision tree in your random forest. Now, some of the additional important hyperparameters we need to be looking at, because random forest itself is now a different model. The first thing we've already spoken is number of estimators. How many weak learners are you considering? Okay, whether to bootstrap or not. Now, I mean, it's an interesting hyperparameter, right? If this is false, all the observations are used in every tree. So for some reason, I don't know what, but for some reason, Scikit-learn has given the option to repeat the data set in every bootstrap sample, which means all 10,000 data points will be used for all trees. I will not do that. Most people don't do that. Okay, but this is something that which the default is true, and ideally we should not set it to false. Okay, we want to bootstrap and we want to control the size of the bootstrap sample. Another important hyperparameter is the size of your bootstrap sample, right? So if I have 10,000 data points in my original data, how many should I use for each bootstrap sample? Should I use 1,000, 2,500? Again, this is also a hyperparameter that we should tune for. Okay, so these two are kind of like the most important, number of estimators and number of or the size of the bootstrap sample. This we will keep it true, right? There's really no reason to keep it false. Okay, yeah, so this is the method that we'll be using, random forest classifier from Sklearn Ensemble, right? And you can see many of the hyperparameters you can see, right? So n estimators is the number of trees, and then you have criterion, which is from decision tree, max depth is decision tree, min sample split, min sample leaf, all of these things are from decision tree. Max features is also from decision tree. And if you remember last time I told you that if you have 6 features, then you do root 6, which is about 2 point something. So you might use 2 or 3 features, random features for each split. Why square root? This comes from some technical and mathematical papers, right? So you can use square root, you can use log, whatever. I mean, when you're doing hyperparameter tuning, you can just put the values and see what works, right? We'll come to that. But typically, this is a guideline that most ML scientists would say, that max features, if you keep square root of the number of features, it works well. right? So we might look for values around that. And as you can see here, we have bootstrap equal to true, which I'm going to leave it as true, obviously. And then here is your OOB score, okay? Out of bag error, it's false by default, but you can set it to true. Random state, we know this is important, right? In fact, I don't know how many of you went through the notebook last time or went through the decision tree classifier documentation, but even the decision tree has a random state parameter. Why? Because of this specific hyperparameter, max features, just because of that. Otherwise, the decision tree is deterministic. Same. If you set the random state, or if you remove max features out of the equation, decision tree will train exactly the same way every time you train it. Just because of the max features, there is a random state parameter in the decision tree classifier also. But we didn't see that because I told you we won't be messing around with max features in decision tree. We'll do it with random forest. So here's the random state to control the reproducibility. Okay. And these are all decision tree, by the way. Everything until now is decision tree except n estimators. And then there's one more here at the end. Okay. Max samples. So max samples, this is the size of the bootstrap samples. So as you can see, the first parameter and the last parameter are ensemble parameters. Everything else in between, these are decision trees. So we will of course do a bit of tuning today, but everyone is encouraged to sort of play around with this and get a feel for what's happening. Right? Here is the documentation for regressor. Once we do the classifier and once you do the decision tree regressor and work that out, this is more or less going to be simple, right? Okay, so that kind of concludes our discussion around random forest. All right, and I feel that it's the right time to introduce this thing, cross validation, because how long are we going to do for loops, right? Even in decision tree, there were some hyperparameters and things like that. Random forest has too many hyperparameters, right? I cannot sit and do for loop analysis forever. And logistic regression, linear regression, there were one hyperparameter. Linear regression had one, alpha. Logistic also has regularization, so alpha, right? There's no need for worrying about tuning that. It's just one for loop, correct? But now that we've come to techniques such as, or models such as random forest, where you saw so many hyperparameters, right? Each influencing how the model trains. It is kind of important for us not to do for loops, and we should use some other kinds of methods. And there is one thing called cross validation. There is another method called grid search. These two are used in conjunction almost always. Okay, so they may be separate methods, but they are almost always used together. So first we'll see what cross validation is, then we'll see what grid search is, then we'll do it together. Okay, now for cross validation, let's go back and remember this slide. Okay, if you remember, we said that the aim of machine learning was that I want my model to become intelligent, right? I want my model to be smart and make decisions the way I'm making. That was the aim. And in supervised learning, the way we did that was we defined our output, we defined our inputs, we then split our data into training, validation, and testing. And training is used for what? Parameters, right? Training is used to optimize the parameters of the model. Validation is used to optimize the hyperparameters of the model. Testing is used to, test the model and see, have I done a good job, right? And finally say that, okay, this is all I can do. And then whenever new data comes, we are ready to use the model to predict, right? So this was the process. And if you remember, we split this data into these three parts, right? Essentially, what happens in cross validation is we don't want to do this split. Now there are many reasons why you don't want to do this training validation split. It's kind of like, for loop. Why should I use for loop, right? So one of the main reasons is training data can be scarce. Okay, you could, whatever training data you have, you want to use it. So removing a bunch of that for validation feels bad. Okay, sometimes it just feels bad. So the idea is there a way to do validation within the training? So let's not do the split. Okay, let's use the training data to do both the fitting and the improving. It is possible to do this, and that method is called cross validation, and we'll understand the process right now, and we'll understand it through an example. So we'll start with two-fold cross validation. Okay, what is a fold? We'll understand later. Like once I explain, it should be easy to understand. Two-fold means you split your training data into two parts. So you can see, for example, here, Aarti, Darshan, Isha, Gayatri, Hemant. These 5 data points, right? I split into one part. And then Jasmine, Lokesh, Monisha, Trevor, Zishan, that will be my second part. So what I'm saying is, you build the model using the first part, the red part, and then validate it using the blue part. Okay, so you will get one performance error from that. You build the model using Aarti, Darshan, Isha, Gayatri, Hemant, and then you validate it by predicting for Jasmine, Lokesh, Monisha, Trevor, Zishan. You will get the prediction errors. So you have one prediction metric. Okay, now do the reverse. Use Jasmine, Lokesh, Monisha, Trevor, Zishan to build the model, and then use Aarti, Darshan, Isha, Gayatri, Hemant to validate the model. Okay, now you get another performance metric. Now what has happened here? You have done 2 training runs, so you get 2 model performance values, and you summarize these two to give you one performance. Now there are many reasons why this is better than the typical training validation split. One of the reasons is generalization. See, we don't know what kind of data is going into my validation. Every time you do 80-20, 60-40, whatever it is, we don't know what chunk is going there. So there is some, non-generalized activity going on there. Some, even though it is random, a different set will maybe produce a different result. So now in this case, since we are using both data sets, right? So when I say both, it's because I split my data set into 2 parts. So here we are using both, which means I'm not giving importance to one higher than importance to other. Okay, that's one reason why I want to do this. It is generalized. Okay, the second thing is I have more validation. Basically, the more splitting you do, the more validation you will get. Correct? So here I have 2 performance metrics. If I did only the train and validation split, I have only one performance metric. So here again, you can average out the performance metric and see, okay, really on an average, how is it doing? Okay, so that's another advantage. And third advantage obviously is that you don't need to waste training data. Okay, so training data is kind of like a resource in machine learning. It's like, gold or oil or whatever, right? You don't want to waste training data. So in this way, you're using all your training data to train the model. Okay, this is twofold, and you can expand the same logic to threefold. And don't worry about the block of text on the right. I'll explain it very simply. So on left side, you have this red, you have blue, you have green. Correct? I've split into Aarti, Darshan, Isha, these 3, Gayatri, Hemant, Jasmine, these 3, and then the 4. Use any one of these for validation, right? So for example, if you keep the red one for validation, the rest of it you will use for training. So from Gayatri to Zishan, you use it for training, and then validate using the red one. Similarly, use red and green together for training and validate using the blue, and then use red and blue for training and validate using the green. See how eloquent this method is, right? So you do more splits, you actually have very close, you're getting to using all your training data. Okay, now you can extend this to k folds, how many ever folds you want, and this is called k fold cross validation. Okay, you chunk it into pieces, take one piece for validation, rest of it use for training, and then for each piece you do the same. So this way, in this case, you got 3 training runs, so 3 model performance, and you can do this with 10 pieces, you can do this with 100 pieces, whatever, right? So this is much more better method uh, to validate your models, rather than just saying 80% of my data is training, 20% validation. I'm not going to there's no change after that, right? That's very rigid. This is very fluid and very eloquent method. So as I said, what is the point? The point is that it's a very efficient way to use all our data, especially in cases where the data is less. You get multiple evaluations of the model. This is very important. You get multiple evaluations of the model, right? So you, instead of one validation performance metric, instead of one validation accuracy, you get n number of validation accuracies. Okay. And this of course helps a lot in better hyperparameter tuning. Okay. Otherwise, what happens is that your hyperparameters can be sensitive to the kind of split that you use. In fact, I would urge everyone to go try that. If you go to decision trees or linear logistic, whatever, just try to remove some data manually. Like if you're using 1000 data points, remove 100 manually. Just go to the Excel sheet and delete 100, and then you see how the hyperparameter changes. It will be sensitive. So how reliable is that? How reliable is my hyperparameter tuning when I do that, right? So that casts a shadow on this method, na? Training validation split. It casts a shadow on that method. Slight amount of, not what you say, doubt. This eliminates all the doubt. So when you do hyperparameter tuning using cross validation, there's no doubt actually. You get very standard results. Okay, and this is generally done using something called grid search. Okay, for the hyperparameters. You can find this method. We'll be using it soon from the Sklearn package. Okay, which now brings me to GridSearchCV, the method. So here is the method from Sklearn, and you can see the parameters. Okay, estimator, parameter grid, scoring, refit, CV. I am underlining the important ones, which I have written down in the bullet here. So estimator is essentially the model that you are trying to find hyperparameters for, right? It could be decision tree, it could be random forest, it could be logistic regression, whatever. It is the final model that you want to evaluate, that you want to validate. Okay, so that's the estimator. The param grid is nothing but it's a dictionary. We'll see that it's a dictionary of the hyperparameter values that you actually want to check for. Okay, so we'll see an example. CV, which means cross validation, CV, this is nothing but K. So CV is actually equal to K. Okay, what we saw before, it could be 2 3 4 5, whatever, right? Default is 5. Default CV is 5. Refit, this is also interesting. Refit, if refit is true, what GridSearchCV will do is it will find the optimal hyperparameter combination that you told it to search for, and it will refit the model using those optimal parameters. Okay, so it will give you the optimal final model, right? It's so much luxury. Correct, so much luxury. It will do all the hyperparameter tuning, right? It will find the optimal values, and then it will fit with the optimal values and give you the final model, right? So just one code cell, imagine, just one code cell for doing all this. Scoring is the metric that you want to use. It could be accuracy, mean square error. It's based on the task. Verbose is very interesting. I usually like to keep this a higher value. It's not a technical parameter, verbose. If you give higher values of verbose, you will get bigger print statements essentially. If you remember some of my decision tree tuning, I manually put some print statements. Training is done, training is done, training is done, something, right? So if you keep higher value of verbose, you will get more information. And I strongly feel the reason they included verbose is because it gets boring. Because when you do GridSearchCV on a random forest for so many hyperparameters, you know how complex the resource, the computational time is. So you'll end up staring at your screen for 5 minutes or 10 minutes or something, right? So I strongly feel they included verbose so that we don't get bored. Anyway, jokes aside, it does give me very important information. We will see that. Okay, so Just a quick example of parameters grid. So here n estimators and max depth. So obviously I'm talking about random forest. So the parameters grid is essentially a Python dictionary, as you can see. The keys are n estimator and max depth. These are the keys, and the values are actually lists. Okay, so this means I want to search for n estimators 50, 100, 150, 200 with a combination of max depth 2 and 4. So geometrically, this is what it looks like. So you have this space of hyperparameter values, right? You have infinite number of max depth, you have infinite number of an estimator. In that infinite search space, I only want to search for these combinations. This is why it is called grid search, because it ends up looking like a grid, right? So I have 4 values for n estimators, I have 2 values for max depth, so 4 into 2, correct? I will have totally 8 combinations that will be searched for. Similarly, if you can do for 3, you can do for any number of hyperparameters. So here I have n estimators 50, 100, 150, 200. I can also have criterion. It need not be just numeric, right? Hyperparameter can be anything. So I can check for Gini, I can check for entropy, and maximum depth say 8 and 16. Now, of course, I'm not drawn that geometrically here because it's kind of hard. But let me try. So n estimators, you'll get 1, 2, 3, 4 like this, and this will go on how many times on the criterion axis? It will go 2 times, right? So I'll get 1 like this, 1 like this, 1 like this, 1 like this, and then max depth is also 2. So now I'll get 1 like this, 1 like this, and then 1 like this, 1 like this. So I mean, 3D is very difficult to draw, guys, but yeah, you will get, how many will you get in this case? You will get a 4 into 2 into 2 intersections, right? So that's 16 combinations, because you have 4 n estimators, 2 criterion, and 2 max depth. So you'll get 16 intersections, 16 unique combinations. So we'll be searching for these. Okay. And yeah, so that's parameters grid. What about CV? So as I said, CV is nothing but K. So if you put CV equal to 2, you'll get 2-fold cross validation. If you put CV equal to 3, you'll get 3-fold, so on and so forth. Default is 5. Okay, and just one important point. The CV is actually fitting models. Let's not forget that. So if CV is equal to 2, then what's happening? Your data set is split into 2 parts, right? And 2 models are being fit and evaluated, right? Suppose this is part 1, suppose this is part 2. One model is fit on part 1, evaluated on part 2, say model 1. Another model is fit on part 2 and evaluated using part 1, model 2. Okay. So this has to be multiplied by the number of hyperparameter combinations that you're looking for. When I say model here, it's the same model, not a different model. Inside CV, it's the same model. So it could be any single model. So for example, one of these models is what? N estimator equal to 50 and max depth equal to 2. This is a single model. If CV equal to 2, this specific model is fit twice, 2 times. So in this case, I have 8 unique models. With CV equal to 2 will be 16 models. Got that? And as you can see, this is the reason it's a very, very rigorous search. So in this case, 8 unique combinations, 50 estimators, 2 max depth, 50 estimators, 4 max depth, 100 estimators, 2 max depth, 100 estimators, 4 max depth. So you have 8 unique models. And if you put CV equal to 2, then all 8 will be built 2 times, right? Because for each model, you're doing 2 models for CV equal to 2. So imagine if CV equal to 5, then 8 into 5, 40 models, correct? This could easily go into 1000s, and typically it goes into 1000s. Okay, 1000 different models are being fit. Anyway, so let's come to refit. I told you, what does refit do? It essentially, gives me the final model, right? So whether to train and return the optimal model or not. So GridSearchCV will find the optimal hyperparameter values from the grid that you gave, right? and it will return the model. Okay, its default is true, by the way. The default is true. Okay, a quick exercise to understand, how many models are being fit. So if n estimators has this list that has 4 values, criterion has 2 values, max depth has 2 values. So you can see those values in the bottom here, 4, 2, 2. Okay, and suppose I do CV is equal to 10. Then each of these 16 unique models will be fit 10 times on the same data set by cross validation. So the data set is taken, split into 10 parts, then 9 at a time you will take, right? So 10 parts are there, take 9 of them, fit the same model, take another 9, fit the same model, take another 9, fit the same model, right? And each time you fit this, you're evaluating on the remaining one part. So for each of the 16, you're fitting it 10 times on the data. So 4 into 2 into 2 into 10. Okay, and if refit is equal to true, then the final model is fit again. So that is again another training. So technically speaking, for this setup, 161 models are being trained. Okay, let's do another example. So suppose I have 1, 2, 3, 4, 5 n estimators. So you can see here 5, and I have 2 values for max depth. And if I don't specify CV, I told you default is 5. Okay, if you don't specify CV, default is 5. So 5 parts in the training data. And suppose refit is false, then it will not fit that last model. So in this case, you have 5 into 2 into 5, which is 50 models. Okay. Yeah. So these are some of the important metrics. Now scoring is something that we will touch upon a little bit today. For classification, we've seen accuracy. We've understood what accuracy is. There are other classification metrics which are important. Now I will guide everyone into one of these in the later part of today's demonstration, right? But I would encourage you guys to go and study about these other classification metrics. See, to be very honest, regression metrics are all the same, right? I think everybody is kind of thinking the same thing. When we did linear regression, MSC, MAE, MAP, I mean, come on, they're all almost the same. Meaning is the same, right? It's how much difference is there? How much mathematical difference is there between the truth and the prediction? That's all it is in regression. What else is there? But in classification, there are different meanings. Okay, and I'll touch upon that a little bit in the demonstration today. But once I do touch upon that and give you guys some guidance on how to study that, I would encourage you guys to go read about this and study about this and even use this. Okay, in the in your models. Anyway, so there is a parameter called scoring in GridSearchCV, right? This is where you can specify the metric you want to use. Okay, so when you evaluate or validate each of those models on the remaining piece of data, what score are you using? Are you using accuracy, MSE, what, right? And also for those who are thinking, why this negative is here, as you can see here in the regression, it says negative mean absolute error, negative mean square. Why negative? So when we do linear regression and things like that, we want to minimize the mean square error, right? Sklearn has has a backend where it maximizes things. Okay, not minimize. So on the backend, Sklearn, Scikit-learn, the library is built to maximize metrics. Therefore, you take negative. Okay, so maximizing negative means minimizing the mean square error. Okay. So it's just a weird thing with scikit-learn. All right. So part one, load packages, load data, pre-process, split into input, features, target variable, training, validation, testing. By now, this stuff should be like, what do you say? You can close your eyes and do this, right? By now, this should all be very obvious when doing supervised learning. And so, NumPy, pandas, matplotlib. I mean, it's so obvious that let me just skip it, right? What we really want to look at is this fellow here. From Sklearn Ensemble, I'm importing something called random forest classifier. The partner to this is random forest regressor. Okay. And performance metrics, we know these already: confusion matrix, accuracy, all of that. I would like to draw your attention to something called a recall score. So we'll see what that is. Okay. So if you remember in scoring, I showed you there are different scoring metrics for classification. There is something called recall. We'll understand what it is. And then from Sklearn model selection, we import this thing called GridSearchCV. Okay. So the new things are these, and these. Okay. So I'm running this. It's the same telecom churn data. You read it, look at the data. We know the columns, we know all of this, right? So I believe we have essentially a telecom company, and they are giving subscriptions to all of these customers. And we have data about these customers, the gender, do they have partner, dependents, how long they're using the service, what kind of service they're using, so on and so forth. And finally, the target variable here is the churn, right? Whether this customer stopped using the subscription or continuing to use the subscription. Okay. So these are all the columns that we spoke about. We know that there are 7,043 data points and 20 features. This includes churn, right? This 20 includes churn. There are no null values. We saw that before. And for those who are interested into a more deep dive of the data, and which you should, right? When you do data analysis, it's important to know your data, right? So it's good to understand what each feature means and sort of think about it that way. Which features should I use, or should I treat features differently? Things like that. For this demonstration, we'll use the same subset that we used before. Just a few columns, right? I will leave the actual data to you guys so that you can, work it out as if you're working on a new sort of project, right? So I'll just do this on a subset. And we know that we need dummy variables for categorical variables. Why? Because random forests are essentially decision trees. So we need to convert gender and all these things into dummies, right? 0, 1. So we do that. Okay, we got our dummy columns now. So dependents no, dependents yes, phone service no, phone service yes, things like that. And then this payment method had multiple levels: bank transfer automatic, credit card automatic, electronic check, mail check. Yeah, these are the kinds of payment methods these users are using. Okay. Yeah. So finally, you do the input-output split, right? So X is your set of inputs, Y is the output, and of course, for the basic part, we will split it into 3 parts: training, validation, and testing. Later, we'll only use training and testing. Okay. So now, after that, you do the split, right? We know how this piece of code works. You do a level 1 split of the data, and whatever remains, you split it again. So from that, you get 3 data sets. So this is the same split that we saw last time. Okay. Right. Can we move on with part 2 after this very, very quick revision of part 1? Please put yes in the chat for part 2. Okay, wonderful. Part 2, basic random forest model. So here what we are going to do is we are going to fit a default model. Okay. So we will not restrict this model, although we will use a random state value so that I can create the same random forest again. And you must be thinking, with so much randomness, how can you recreate? You can. Okay. Essentially, these are all pseudo random numbers, right? These are not actual random numbers. Computers can generate pseudo random numbers, which all start with some seed number, right? So if you do a deep dive into NumPy random method of Python, if you go deeper into the programming aspect, you will find that there is a seed value. From that you get random numbers. So yes, you can reproduce the same random forest again and again and again. Okay, so we'll set that value to 0. Interestingly, in machine learning, people like to set it to 42. I don't know why. You can do that, but I'm setting it to 0. Right, so I'll just fit it without specifying any hyperparameter. Now, before I fit it, let's look at the documentation. See, n estimators, criterion, max depth, and all of that. See the default values. Okay. So for n estimator, the default value is 100. Criterion is Gini. Max depth default is none. Okay. All my trees are going to, go till max depth. Interesting. Min sample split is 2. Min sample leaf is 1. We know what this means. Min sample split means if a decision node has, at least 2 data points, we can split it. Correct? That's what this min sample split means. What is min sample leaf? The minimum number of samples in a leaf should be 1, which is always going to be the case. You can't split 1 anymore. So this again is a very overfit condition. Correct? These are very overfit conditions. Max features you can see in random forest, it is square root. Correct? Max features is square root. So let's just quickly do one thing, right? I want to import decision tree class. Sorry, it's not from. Sorry, Sklearn.tree. I want to import decision tree classifier just to show one point. So here in part 2, I'm starting off with this RF model 1. So before that, I'll just show you one thing. Right? If I just check here for decision tree, see the max feature default value. The max feature default value is none in decision tree, right? So the developers of decision tree themselves, so conceptually the idea was that in the decision tree, if you use random feature subsets for splitting, it will handle overfitting, but it doesn't work that well with decision trees. That's the point. So the max features parameter for decision tree default is none, and random state is also none. See, so these two things are practically unused in decision trees, but the same default, if you see in random forest classifier, where is it? Yeah, max features is square root, not none. So if you have 6 features, how many features do I have in my data set? I have 1, 2, 3, whatever, around 10, around something like 10 features, right? So in the random forest classifier, what's going to happen is it's going to use max features equal to 3, right? Square root of 10 is around 3. So each decision tree inside will be splitting with 3 features to search for, 3 random features that it will search for the Gini index split each time. So just wanted to show you guys that the default of the same hyperparameter in decision tree in decision tree is none. In the random forest, it is square root. So that's how important randomness is in random forest. Okay, so that's one thing. Then what are the other things? So number of trees default is 100, number of estimators. Max features is square root, and I guess I've written auto here. It's probably square root. Sorry about that. Right? You can check the default just by checking the documentation like this. Right? You can check the default is square root for max features. True for bootstrap. Let's check that also. You go down. Bootstrap is true. So yes, we will be bootstrapping, my data set. Out of bag score is false. And yeah, there are many of these other things. And notice that random state is none. Okay, so if you don't set it, it will be different random forest each time, which is okay if you are not doing analysis. If you're doing, only ML model building and things like that, that's okay. But when you're trying to analyze your model and make sure it's working properly and all that, I would suggest analyze it first with some random state value. Okay. Anyway, so these are some important defaults that you have to keep in mind. Now let's do the same thing. You just need to instantiate the class. So random forest classifier is a class. You instantiate it into an object, RF model 1, and then you use the fit method call of the object. Okay. So now you can see that my random forest classifier has been fit. Similar to decision trees, random forest also gives you feature importance, right? Based on how many times the feature is coming up and how the Gini index varies with that feature split, so on and so forth. It produces for you a list of importance values, which you can obviously just match with the index of your data and then sort it out and print it in a very neat way. Okay. So the random forest also says that monthly charges and tenure are the most important uh, features to use. So essentially what this means is that if you don't if you are happy with the accuracy that comes from two features, then you can actually drop all the other features. That's what this means from a machine learning point of view. From a data analysis point of view, this means that I need to find out what's going on here, right? So my monthly charges, so I am the company, right? I am the telecom company. This is telling me that my monthly charges influences whether a person leaves or not. So then I need to find out, what's wrong with my charges. Are my customers unhappy with the kind of charging that's going on? Should I, create a different kind of payment scheme for my customers, right? So these are the questions that comes to your mind when you say monthly charges. And tenure, this is also very important, right? From a data analysis point of view. I think my customers are getting bored. That's what this means, right? If tenure is a high importance feature, which important in what? Important in explaining the variance in the churn feature, which means it is important to predict yes and no churn. Okay, and this immediately tells me, if I had some knowledge, if I am from telecom background, or if I know something about telecom, right, I would say that, are people getting bored after 5 years, after 10 years? Are they just leaving? They don't want my service anymore. So that's how you can use decision trees and random forest purely for data analysis purpose, right? And then you can actually look at the trees and do a bit more detailed analysis. And from a purely machine learning point of view, I told you, right, if this is explaining so much of the variance, then do I really need all these other features? So that is actually a question between complexity and accuracy. We'll come to that. Okay. Anyway, so now you can obviously build the confusion matrices for this model. So we'll build for training, we'll build for validation also. So as you can see, and this is expected, right? The default random forest, the default trees inside the random forest were already built for overfitting. So clear overfitting is going on, right? Almost 4,000 something out of 4,000 something, you're getting matching predictions, right? So on the y-axis, you have the true value, whether the customer really churned or not. And on the x-axis, you have the prediction from the model, right? And it has been correct some 4,200 times out of some 4,200 times, right? So that's very high accuracy on the training data. Validation, not doing that well, right? You have many more errors. So errors you can actually find in the alternate diagonal, right? The not the principal diagonal, the other diagonal. So here you'll get the errors, correct? And these errors will be more important as we do different kinds of data analysis in classification. These errors will be a bit more important. We'll revisit this a bit later. So as similar to decision tree, the random forest also predicts probabilities. I told you last time also, the decision tree does not really know what it is saying. Okay, and in the end, it is not saying that this leaf node means customer churn. Yes, the decision tree doesn't know English or language for that matter, right? It's essentially predicting a probability. Based on the probability, we have programmed the method to assign the label, yes, no, whatever, that we are doing that. Okay, so similar to decision tree, random forest also actually gives you predicted probabilities of category 1, category 2. So here category 1 is yes churn, category 2 is no churn. Okay, positive label and zero label. So what's the probability of churning, probability of not churning? That's how these values are. Okay, so you can see for this data point, and by the way, what are these rows? These are nothing but the data points. So I just print xtrain and I'll just print the first two. Sorry. So I have these two customers, correct? These are my xtrain values. and you can see white train also. Sorry. So I have these two customers, 5339 PXDVH, 5339 PXDVH, these two customers, same customer, and then I have 8821 whatever, I have 8821. Okay, we have two customers here. As you can see, the actual value for both these guys is no churn. Okay, actual value is no churn, and the prediction is no. And I guess I made a mistake. The first one is here is no, and the second one is yes. Okay, so the third customer here 0.12 0.88, that person must really have churned. Yeah, so you can see here 3583 EKAPL, this person has churned, and the probability of yes is 0.88, probability of no is 0.12. So similar to decision trees, the random forest also gives you predicted probabilities. Now using a method called predict, you can directly get the predictions. Okay, so predict proba, this is the actual mathematical end of the decision tree or the random forest model. Okay, mathematically that's where it stops. After that, it's all about labeling. Okay, so I convert the majority here into the label. So 0.88 probability of yes churn, therefore this person churns. That is a prediction. So that you can get from the predict method. Okay, so here again you can predict for train and validation. Let's check the train preds. So we saw no, no, yes, yes, right? So here it is no, no, yes, yes. See, so this probability is higher. 0.75 is no probability. So the prediction is no. This obviously is a very 100% probability for no. So the answer is no. The prediction is no. Here the no probability is less. Yes probability is much higher. Therefore the prediction is yes. So this is how predict works. Okay. And now that you have predictions, then you can build this confusion matrix. Okay, there's a reason I'm explaining confusion matrix, predictions, and all these things in a little more detail in this session rather than the previous session, because in the previous session we wanted to focus more on the model, and now that we know the model and random forest being a very simple method, we want to spend some time on actually the meaning of classification, right? So we'll spend a little more time in this demo on that. So once you have these predictions, you match it with the true labels, right? So that's exactly what's going on. How do you get these numbers? You get it by matching the true values with the predicted values. And you can get, the confusion matrix as a mathematical object using this method called confusion matrix. Okay, cool. And there's, of course, I can go ahead and calculate accuracy using a simple formula from here, right? But there is also a direct method from Sklearn called accuracy score. So in that also you just give your train predictions, train true values and train predictions, and you'll get your training accuracy. Similarly, you give your validation truth and validation predictions, you get validation accuracy. This was expected, I think. Training accuracy 99.5%, validation 77.7. I mean, it's not a bad validation accuracy, but I mean, it's so clearly overfit that how am I supposed to trust this model, on unseen data, right? Okay. Yeah. So part 3, now we'll start restricting these models because there's clear overfitting going on. And we remember all this, right? I mean, we know how to do all this. Notice that each time I have to keep the same random state so that my analysis is comparable. So if I want to compare RF model 2A to RF model 1, I have to compare it with the same random state. Okay. So let's start with number of estimators. Okay, number of trees. Let's start with a very large number of estimators, 500 estimators. Okay. So n estimators equal to 500. Note that the default is 100, right? So default here is 100. I'm using 500. You can see it takes time to fit. I think that's very clear, right? It took a lot more time to fit. Now the model has been fit on the training data. So, we can do the same thing, prediction, accuracy, and put it in the data set. Okay. Sure. it's still overfitting. Okay, this thing is still overfitting. Okay, obviously it's way too many estimators. Now suppose I use a smaller number of estimators. You remember I told you in the beginning of the session that if I use very few estimators, then most likely you're going to get underfit. But at the same time, remember that the hyperparameters for the decision tree, they are all overfit hyperparameters. Okay, so we may get good random forest, but most likely it's not going to be as good as these. Let's see. So you fit it. I'm using only 5 estimators, and let's have a look at how it did. It did little worse. Okay, it did slightly worse. And why only slightly worse? Why not very bad? Because I told you the decision tree hyperparameters are all overfit hyperparameters. Okay, you did not control the maximum depth, did not control min sample split, did not control min sample leaf, right? So these are all overfit hyperparameters. So although your number of estimators is less, your estimators are not weak. Okay, in this case your estimators are not weak. All right, let's look at another important hyperparameter, which is the size of the bootstrap sample sets. Now for this I really need to look at xtrain, or at least just length of xtrain, right? 4225. So I have 4225 data points. Okay, now notice that okay, so the hyperparameter name is max samples. Okay, by default I believe it is where is it max samples, none, right? Yeah, none means it will use the full data set. Okay, so by the way, that also leads to overfitting. So you can obviously give integer here. So you have 4225 data points, you can actually give something like 1500, right? So you're saying use 1500 out of those 4225 for each bootstrap sample, give me a data set which is 1500 in size. Or you can also use a fraction. So if you say 0.9, what you're saying is you want 0.9 times length of xtrain, which is 3800 size for the bootstrap samples. Okay, so let's go for a very large size, 3800, right? Let's use 0.9 as the percentage, 90% of the original data, right? That much size bootstrap sample I want, and let me fit it. Okay, and then let's find how it's performing, on the training and validation data and all that. Same thing, right? No improvement, absolutely no improvement. As you can see, till now it's all just very amazing training accuracy and really bad validation accuracies. Okay, what happens if we use very small bootstrap sample? So in this case I'm using 0.2. So length xtrain, right, star 0.2, 845, which is still large to some extent. I mean, considering that these are random forest models, if you have 4000 data points, you're using 800 size bootstrap samples, which is still moderate. I won't call it small, it is moderate, but still let us see, with smaller bootstrap sample what's going on. Okay, finally we can start breathing a little better. With smaller bootstrap samples, your estimators have started becoming weak, which is what we wanted. Okay, your estimators have started becoming weak, which is why your training accuracy has now gone to 86%. But note that the validation accuracy has started to show some promise. Okay, I'm not saying that this is the best hyperparameter, guys. For different data sets you will see different behavior, but this is just giving you a sense of how things work. Next, tree depth. This is, I just wanted to put one hyperparameter from trees. Okay, and we already know max depth equal to 8 has to overfit. There's no doubt here. Okay, if you use max depth equal to 8, it has to overfit. And you're getting 83 and 80, right? That's very interesting. That's very interesting. This tells me, what does this tell me? Okay, let's analyze this. So I have 83% training accuracy and 80.5 validation. This is actually very good. Now we were expecting this to overfit. Why is it not looking like it is overfit? There's a reason for that. Maybe that the max depth of the original tree is much higher. So we are saying max depth equal to 8 is a large depth. But maybe if you don't specify this value, the trees are actually fitting till max depth equal to 20 or 30 or 40. I don't know the depth, right? So how do I know 8 is a high value? So here you can actually try it again, right? For max depth of say 20. I'm not sure whether it will fit. Yeah, it's fitting. As you can see, if you take max depth equal to 20, now again it's gone to overfitting. So max depth equal to 8 was a guess, right? It was a guess. Our minds are thinking, okay, 8, 9, 10 level of the tree is high value, right? Not the case. When you have so many features and so many data points, it's not the case, right? So let's go ahead with 20 itself, right, for the large tree depth. As you can see, it's overfit. Okay, so this means that we need to look at max depth, right? Lower max depth is controlling my overfitting to some extent, so that's good to know. Okay, what will happen if we use a low value? I've written high here. What will happen if we use a low value for the max depth, like 2? Let's see. Yeah, it is starting to underfit. It is generalizing. It's not bad, it is generalizing, but it is starting to underfit, right? When I can get 78% validation or 80% validation, why should I be happy with 74%? So again, we'll just go fast in these parts because we've done this before. I'm defining a range of tree depths to tune over. I'm using a for loop. I'm fitting a random forest classifier with the particular tree depth. I'm recording its performance and I'm putting it in a data frame. That's all. So let's just go ahead and do that. Okay, it's done, I think. And of course you can use the validation and training accuracy for different tree depth values and see how it's going on. Now after max depth 6, it's a clear sign of overfitting, right? It's you can see the gap between the training and the validation is just going on increasing, right? In fact, it's very weird. The more that your training increases, the more validation decreases. So you have departed from intelligence and you have gone towards memorizing. Okay, that's what's happening here. This is all overfit. And here, and by the way, sometimes you will see that validation may be higher than training. Okay, for example, see max depth equal to 3, max depth equal to 4. Validation accuracy is more than the training accuracy. That's not a good thing in general. It just means luck. Okay, this is just lucky, nothing else. What we really are looking for, we are looking for generalizability where the two values are almost the same, right? So I can see max depth 5 and 6 as good values. All right. Similarly, we can do a tuning for number of estimators. Now see, estimators, I've taken NPA range 4 to 100. So 4, 8, 16, so on and so forth. The generally suggested values are like 25, 50, 75, but I wanted to do a bit more step-by-step analysis. So I'll be doing a bit more fine resolution. Okay. So again, same thing, you create the range you want to tune over, and you fit a random forest classifier for that specific value, and just fit it and get the accuracy scores and all of that. So as you can see, it's fitting. Okay, 4, 8, 12, 16. This is going to go till 100. And let's see what's going on. Okay, is it done? It takes a bit of time to run. And you can see a very weird graph, right? This is very weird, right? As in, it's not as beautiful to look at, right? This is very nice to look at. There's very interesting things we can comment on this. Is there anything interesting we can comment on this? Doesn't look like it, but yes, there is something very interesting we can comment on this. What I can comment on this is that your training accuracy is not changing much after a certain number of estimators, which means that the number of estimators is not leading to the good training. Let me repeat that. So after 24 to 28 estimators, that is trees, right? So 24 to 28 trees around here, the training accuracy is almost the same. This means that you increasing number of estimators is not helping, right? So estimators did not help. So there is something else that is producing such a high accuracy value, and we know what that is. It's max depth, it's min sample split. None of that has been tuned for, and because of that you're getting this very, very, very high training accuracy, and you're almost getting a much lower validation accuracy. So what should we do? Suppose we control one of those things, right? Suppose we control maximum tree depth at 6, which is what I have done here, right? In the previous case we did not control that. Here, right? So I want to control max depth, and then I want to tune for number of estimators, and then let us see what happens. Remember, ensemble methods work on weak learners, not strong learners, right? So I'm making my learner weak by restricting maximum depth. Now let's see what it looks like. Now I can see a much more informative training history that's going on, correct? So with a weaker learner, what's happening now you can see. So here, this is not good, obviously. There's a bit of overfitting and things like that going on here. Here it's crossing and then coming down. Here it's again crossing, coming down. But these are safe values, right? Around this range is what I would say is safe, because it's kind of stable, right? The training and the validation accuracy are more or less stable. But at this point, I think you're starting to understand that this is a very cumbersome process, right? Taking pair by pair, analyzing one by one, then building these graphs or getting these values, then analyzing which of these should I pick. It's very cumbersome. When you have so many hyperparameters, it is cumbersome. At this stage I can say something like, okay, number of estimators 60 with maximum depth 6, or number of estimators 76 with 6. But did we check for everything else? Did we check for min sample split? Did we check for all the other hyperparameters which influence my training? We did not, right? Which is what leads me to GridSearchCV. Okay, so which allows for good, efficient hyperparameter tuning for combinations of hyperparameters. From here on, we don't need separate training and validation data, so we can go ahead and combine that. Let's call it X-train CV, Y-train CV. So you can use pandas concatenation to just join those two, the training and the old training and old validation. Okay, so now you combine 4225 plus 1409. So now you have 5600 training data. Okay, now here comes the fun part. So what you do is, first you focus here. Okay, you forget all this, focus here. GridSearchCV requires a few things from you. Okay, by the way, this is also a class. GridSearchCV is also a class, so you have to instantiate it, initialize it, and put it into an object, right? That class has to be called as an object, and then you can use methods associated with the object like fit and other things, right? And as you know, objects will have methods, attributes, and all that. So that's what's going on here. Okay, so first you look at this class call. It needs a few things from you. It needs your estimator. What is your learner? What is your base learner or base model? That you need to specify, okay, to your GridSearchCV. You also need to specify this parameter grid. These other things, actually, by default, GridSearchCV is able to use defaults and inferred values, right? Based on the kind of target Y-train, it can automatically default, it will use accuracy, right? CV default value is anyway 5. Verbose, I don't know what the default value is, but whatever. Verbose is not really important. The most important thing it needs from you is these two things, right? The estimator that you're going to use. So that's the one on which the different hyperparameter values will be put and then trained n number of times, right? Here n is equal to 5. So let's go to the estimator first. Here is the estimator. So my base grid model, which is the estimator that I want to use, I'm just giving it a name. It is a random classifier, random forest classifier with random state 0. Now this random state 0, I can put it in my parameter grid also, by the way. If you want any of these hyperparameters to be constant, you can put it here in the base model. Okay, and then you enter that model into the estimator parameter for GridSearchCV. So if I want n estimators only 100, right, then I can just put that value inside here, right? I can just do n estimator equal to 150. Why not 100? Because 100 is default, so then I don't even need to put it, right? But if I put it here, then it will not check different values. Each model that is checked in GridSearchCV will have 150 n estimators, correct? So if you want anything to be constant, put it here. What are the things you don't want to be constant? Those are the hyperparameters that you want to tune. That you put it into a dictionary like this. So here, as you can see, I am at least looking at some of the hyperparameters which I think are not letting me generalize my model, such as n estimators, maximum depth. This is the tree depth, obviously. Maximum samples. Max samples, what is this? The size of the bootstrap. So if you remember, we took 0.2, that was okay. So I want to check 0.1 also. Max features, we didn't check for this anywhere, I think. And in fact, let's quickly check the xtrain, what is it? Xtrain CV dot shape. Yeah. So I have 13 features. According to the the academia, root 13 is a good value. Root 13 is around 3 point something. So max features I want to check for 3 and 4. Okay. I can check for 2, 3, 4, 5, but I'm just demonstrating 3 and 4. And min sample split, I'm using fractions, obviously. So train CV length, right? This is some 5,000 something, right? Yeah. So this into 0.005. How much is this? 28. Okay. So min sample split, I'm checking for 28 and 56, basically. This means what? If a node has less than 28 data points, it will not split that node anymore. Okay. So I'm checking for 28 and 56. You can, of course, check for larger values if you want. So now if you see how many combinations am I going to get? I have 3 values here, 2, 2, 2, 2. So that's 3 into 2, 6. 6 into 2, 12. 2s are 24 into 2, 48. I have 48 combinations. So 48 unique random forest models, which will be checked 5 times because CV equal to 5. So 240 models we will be checking. Okay. And of course, refit is default, which is true. So it is going to return my optimal model. So I can save that optimal model in a new variable. I'm saving that in grid model. Okay. So let's run this. Now this is where the fun starts. So if you run this, you can see it says fitting 5 folds for each of 48 candidates, totaling 240 fits. And you can see each fold for each candidate. Okay. So yeah, this is the first fold out of 5 fold for this specific combination, which is max depth 5, max features 3, max sample 0.1, min sample 0.005, and estimator 60. Same thing here, you can see same thing. Max depth 5, max features 3, max samples 0.1, min sample 0.005, and estimator 60. So you'll see this 5 times, right? You'll see this unique thing 5 times, and then you will find a different one. So here max depth 5, 3, max samples 0.1, and n estimator 80. Okay, so now you have a new random forest. So this is a different random forest, and then again you have a different random forest. How many such different random forests? GridSearchCV tells you 48 candidates. So you have 48 different random forests fitting 5 times. And here are your accuracy scores. For each of those fits, you will get an accuracy score. What GridSearchCV does, it takes the average of a certain model. So this model, which is fit 5 times using 5-fold cross validation, it has 78.7 accuracy, 78.2, 77.8, 78.5, 79.8. So you take the average of these. That will be the average accuracy of this model. Similarly, you take the average of these, you'll get average of this model, so on and so forth. And in the end, it's going to refit, and the end is very, very, very far away. As you can see, right, this is the most efficient way to do hyperparameter tuning for n number of hyperparameters, right? Yeah, that's that. And now I think it is done running. Yeah, it's done running. So it has fit 240 models, and it has given me the optimal model, that is the 241st fit it has given me. So that model is now fit. So if you just take this object, you can see that it has a list of attributes and methods, right? You have so many attributes: best estimator, best index, best params, so on and so forth, right? So these are all attributes after fitting. Okay, some of these attributes we want to see, right? We want to see best score, we want to see best params, and all those things. So let me just, yeah. So as you can see, these are the main two parameters that we used. And here scoring, I forgot to mention, I think, yeah, scoring I've used as accuracy. Okay, that's why it's giving me these values. Anyway, so now I can get the best score, the best combination of parameters. So basically the best estimator, right? I can get which random forest model did GridSearchCV find out did optimally the best, right? So I just run this and I get this model. So this model has 79.7% accuracy, almost 80. Now, if I compare this with the decision tree from last time, I believe that that one had 78.7 or 79.1 or something like that. So you have 0.006 or at least 0.01, say 10% difference, that is 0.01 accuracy difference. Now I'll come to that point. Okay, I'll come to that point. The optimal number of trees, it says, is 80, tree depth is 6, size of bootstrap sample is 0.1, so on and so forth. Okay, so you have your optimal model, which has been validated with a validation accuracy of 79.7. And it is expected that, that this does well. When I say well, it has to do almost the same as 79.7, right? If this accuracy score for the testing data is way different from this, then there's a problem with the training data, or there's a problem with the parameters that you are checking. But the latter is unlikely, because with the hyperparameters, if you are getting 79% validation accuracy, then that means you have to get around the same in the X test. And if that's not working, either it's not the right model for you, or there is something wrong with the training data. Okay, let's check what is doing on X test. 78, not bad. Okay, not bad. 79.7 here, 78 here. Okay, not bad. Now, to go ahead with recall scores and other such derived metrics from confusion matrix, you cannot use yes and no. You cannot use the original string output values, because these are slightly more mathematical, right? So Scikit-learn can handle accuracy values in those cases, but some of these advanced metrics it cannot handle. So you have to convert them to one-hot encoding, basically, right? So you have to replace no with 0 and yes with 1. And why 1? As I said, the recall score by default focuses on 1. Okay, so by default the focus for recall is 1. So if you replace no with 1, then that means you are focusing on the no class more. Okay, so let's go ahead and replace. Okay, let's replace the y values, both train and test. We will replace no with 0 and yes with 1. Okay, and let's go ahead and do the same analysis again. Nothing else is different. The only thing I changed, even this is not different. I didn't do anything to my output data. Okay, it's the same. Replace no with 0, yes with 1. That's all I did. The only difference here is scoring. I'm changing this to recall. Rather than accuracy, I'm changing to recall. Okay, and let's see. You can already see the scores are really bad, which is expected, right? You go back to your original analysis. What is 175 out of 175 plus 196? So recall, I think, is defined, but I think you should go and check this more mathematically. But 175 divided by some total of this, right? 370 something, correct? So that's around 40-50%, isn't it? And that's exactly what you're seeing here, right? You're getting even worse actually. 30, 20, 30, 20, 36%. These are all really bad recall values. Yeah, these are all pretty bad recall values. Okay, it's still running. And again, You can find out the optimal model here. Okay, I'm getting somewhat 40%, but is this good enough, right? If you're building the model for the business problem statement that I need to predict which of my customers are churning out, and I need to develop an intervention plan for those potential customers. If that is the business problem, then you cannot use accuracy. You have to use recall or a similar metric from the confusion matrix. Okay, this is done. So let's see the optimal model here. So it is giving me some optimal model, right? And I'm getting a recall score of 42%, which is obviously not good. If you are training your model to actually focus on the people who are leaving your company or the service, right? In the sense they're leaving the subscription of the telecom company, then I should get a very high recall score. Okay, and I'm getting 42%, which is bad. Coin toss is better than 42%. If I just flip coin, and that's 50-50, isn't it? So what use is this to me, right? So, and you can of course check it on the testing data. I get a 43% recall score. Okay, and this is where I would give you guys a bit of additional hints. I've already given a lot of hints, right? One thing is you use the class balance, class weight parameter. That can help you a little bit, but more importantly in this case, I would urge all of you to go read about all the derived metrics from confusion matrix. You have recall, you have precision, and things like that. Okay, you have different metrics which come from the confusion matrix, which focus on different parts. I just showed you the accuracy focuses on what? It focuses on the principal diagonal, correct? Accuracy focus on the principal diagonal. There are business cases where accuracy is important, sure, but most cases you will see that in classification, when it comes down to business problems, you will be focusing on either the negative or the positive class, right? And if you want another example, think about medical testing, right? Suppose there's a diagnosis of a certain disease. Just think about it, right? Which cases are risky, which cases are okay. If you do have the disease and the diagnose predicts you have the disease, good, that's a good thing. If you don't have the disease and diagnose predicts you don't have the disease, that's also good. If you don't have the disease and the diagnose predicts you do have the disease, little bit loss for the doctors, still okay. Little bit loss for you also, it's okay. But if you do have the disease and the diagnose does not predict that you have the disease, that's a very dangerous case. So then if you do your analysis and say I have a high accuracy, it's not going to work, right? So I just wanted to spend some time at the end of this session just pointing out that accuracy is not such a great deal. It's not a big thing, right? In various business cases, you have to choose what you're focusing on. And in this case, for example, I've used recall. And I would urge everyone to, do the analysis using the raw data, right? The original data, you do the analysis and try to get, a better recall score, because that's what this business problem demands. Okay.
Great job making it through this tutorial. You now have a strong foundation in decision trees and ensembles. You have learned how to build, tune, and interpret these models. The key takeaways are that individual decision trees are simple yet powerful models that can handle both classification and regression tasks effectively, while ensembles can significantly improve model performance by combining multiple trees. The dataset and code used in this tutorial are added in the description for you to check out. Don't be afraid to experiment with different parameters and datasets. Keep practicing, and I'll see you in the next video.